Hello. I think if you are not saying anything, we won't see the transcript. Okay, I can see the message. Good afternoon. Please, can you all see my screen? Or can anyone see my screen?
Yes, okay. We can see your screen. We can see your screen.
Okay, great. Thank you.
Yes.
Okay, thank you. I think we'll start in some minutes. Yeah, thank you, everybody.
Good afternoon, everyone.
Good afternoon.
Thank you. I was just testing my mic.
Come on, Renata. Oh, you're muted.
No.
Yeah. Right.
Oh, time to start, right?
Yes. You want to share your screen?
Yeah, I will share my screen. Oops. Oops, not yet. Not yet. Let me speak a little bit first. Good morning, friends in North America and Africa. It's a huge pleasure to be here and welcome you to our second virtual workshop. So now let me share my screen. Welcome to the second workshop of the USAfrI Initiative in Electronic Structure. It's a huge pleasure to have you all with us today. This workshop is now today being hosted by Columbia University and the ICTP in East African Institute for Fundamental Research in Kigali, Rwanda. Well, the world has changed a lot since US-Africa initiative. It was launched in 2019. And while it has become more difficult to travel internationally and meet in person, we also developed more practical, egalitarian ways of interacting virtually. And this workshop is an example of it. The USAfrI initiative is one of the 4 initial projects or grants of the American Physical Society Innovation Fund Award. And as I said, it was launched in 2019. And the goal of this project is to support fresh approach to serving the physics community in line with the society's strategies. And these strategies are based on promoting its mission and strengthening its foundations, its missions, to serve its members, the physics community and society, and ensuring a meaningful role of scientific research dissemination. And strengthening its foundation is increasing organization excellence and securing its sustainability, its financial sustainability. And the USAfrI initiative was really in line with these priorities, these goals of the American Physical Society. It's an exemplary project that is being really praised by several around the world that I know. Friends in other communities to whom I have introduced this project, and this might replicate across other societies as well, this type of initiative. So the PIs in this project were Omololu Akin-Ojo, director of the ICTP in Kigali, Rwanda, Sinead Griffin, staff scientist at the Lawrence Berkeley Lab, Richard Martin, professor at Urbana-Champaign and Stanford University, and myself, professor at Columbia University. I think I was the latest addition to this group that had already been working together for over a decade. And so the USAfrI was created as a platform for exchange between African and US physicists to create major opportunity for impact in research and education in Africa. And we chose, of course, electronic structure was a choice because it had applications in many fields and also tapped from the
Recording in
network
progress.
in Africa that had been sustained for over a decade, the ASISMA, the African School of Electronic Structure, Methods and Applications, a network in electronic structure in Africa. So our proposal to the American Physical Society consisted in 2 in-person workshops, plus research visits of African researchers to the United States, and possibly exchange to African as well, US researchers in Africa as well. So the first workshop was supposed to have happened in person in Rwanda in 2020 and happened in June 2021, and we know why, because of the pandemic. And the second USAfri workshop was supposed to have happened in the US in person in 2021, and now it's in virtual in 2022. But the third item of the proposal, the research visits of African researchers to groups in the United States, will start happening next week. 15 of you will come to the United States. 15 of you will come to the United States to participate in a workshop and then follow up with research visits across the United States. And hopefully the other five people will come by the end of the year. And we are eagerly waiting for your visits here. This whole enterprise has been made possible with all its uncertainties and turns and twists that we have to adapt to make it possible. Several wonderful people have made this happen, worked very hard to make this happen. Amy Young at University of Illinois, Stephen Nenge at ICTP in Rwanda, Christina Rom, Stella Laujinji Zhuang, and Konstantin Cherniak at Columbia University. These are the people who have worked very, very hard, in addition, of course, to the PIs, to make this meeting and these research visits possible. So without further delay, I will pass the word to Omololu. So thank you all for being here and your interest on the project.
Okay, thank you very much, Renata. Okay. I'll share my screen. Okay. So I'll just say a few words and then I will introduce our speaker. So just like Professor Renata said, this USAfri initiative on electronic structure sponsored by the APS Innovation Fund. So this is one of the APS Innovation Fund that was sponsored a couple of years ago. So we're one of the first four that got the APS Innovation Funds. So it's sponsored by APS, the American Physical Society. So we had a few meetings in the past, and we're having another meeting now. This USAfri builds on some of the things that we've had in the past. Okay, one of the things that makes it that facilitates our meeting together is the fact that we have had ASESMA, the African School on Electronic Structure, Method and Applications, in the past. So we've been successful in training many people in electronic structure methods, and many of these people have gotten their PhDs and are working in different universities. And this is an initiative, USAfri, to be able to bring together different people from Africa and the US to work together and do high quality research. So this program is definitely separate from ASESMA, but it's hard to talk about the achievements we've made in Africa in electronic structure without mentioning ASESMA and all the programs that ASESMA has had in the past since 2012 up to this time. So in So last year, this program this USAfri program was supposed to have been held in Kigali, Rwanda. We still had it in Kigali, Rwanda in a sense, but we had it virtually. So now, the one we're having now is supposed to be held in Columbia University. We're having it in a way in Columbia University, but we're having it virtually. And so I still hope to extend our invitation to you to visit Kigali. Who knows, you can visit Kigali this year or next year or sometime in the future to visit our institute. Our institute is one of the people supporting and supporting this initiative, USAfri. So our institute is the CTP, East African Institute for Fundamental Research, and is funded by the government of Rwanda in collaboration with ICTP and the University of Rwanda. And there is one more thing I need to say. It would be good to have more partners. Okay, so as partners, it doesn't have to be financial. The financial supporters is mainly the APS. Okay, but it's good to be part of us in the sense of having you as a strategic partner. So currently, we are collaborating with the National Society of Black Physicists. And of course, I already mentioned ASESMA and the African Light Source. And it would be good if the institution you belong to or the organization you belong to can be part of our strategic partners. Okay. We're not asking for funds at this time, but we are saying we could just partner together and achieve a lot in our collaboration between US researchers and African researchers. So before I introduce our speaker today, I'll just give you the program at a glance. So the program will run for 3 days, this USAfri workshop. Today's is the one we are doing now. We'll have a keynote speaker, and then there'll be a session on molecular and chemical systems for energy. There'll be a second session on surface functionalization and low dimension systems. Then tomorrow we start at the same time. We'll have an invited talk, and then a session on functional oxide and perovskite. We'll have another invited talk, and then we'll talk about the hot topic of quantum materials. On Friday, we'll similarly have 2 invited talks, but we'll have some other discussions that different people will take the opportunity to share different things with us. Particularly the editor of physics, Dr. Magero, will be around to discuss with us on science communication. So with this, I will introduce our keynote speaker. So I'm going to introduce Professor Sossina Haile. I don't know if she's there already. If she's there, maybe she could share her screen.
I need you to unshare.
Oh, sorry. Thank you. I'll introduce you. I will share and then I will introduce you. Yeah. Okay. I think I'm on sharing now. Yes. So I'll say a few words about Professor Sossina while she's sharing. Actually, a long time ago, I met Professor Sossina in Abuja. So that was sometime between 2012 and 2015. So she was there invited by Professor Wole Shogoijo to teach us on electrochemistry then. Okay. So Professor Sossina Haile, she's the Walter P. Murphy Professor of Material Science and Engineering at Northwestern University, where she also holds appointments in applied physics and chemistry. She joined Northwestern University in 2015 after 18 years on the faculty at Caltech. Professor Sossina's research broadly encompasses oxide materials for energy technologies. She has established new classes of fuel cells with record performance for clean and efficient electricity generation. She has created new avenues for harnessing sunlight to meet rising energy demands. Among her many awards, in 2008, Professor Haile received an American Competitiveness and Innovation ACI Fellowship from the US National Science Foundation. The 2010 Chemical Pioneers Award of the Chemical Heritage Foundation, and the 2012 International Prize in Ceramics of the World Academy of Ceramics. Professor Haile is a fellow of the American Ceramics Society, the Materials Research Society, the African Academy of Sciences, the Ethiopian Academy of Sciences, and I should add the African Material Research Society. She serves on many editorial boards. So join me in welcoming Professor Sossina Haile to give the plenary talk for us today. Thank you very much.
Okay, thank you for the kind introduction. And it's my pleasure to be kicking off this meeting. I presume you can hear me and you can see the screen?
Yes, perfectly.
Take that. Okay, great. So I'm going to talk about some of the things that we've done with the compound based with Ceria. And I call it the splendid redox chemistry of this material. And let me start off with just saying, why it's important or reflect upon the incredible number of, researchers that are involved in this material, from physical chemists, chemical engineers. I'm obviously a material scientist, applied chemist. It has a vast range of applications because of this splendid redox chemistry. In my lab, we use it as a fuel cell electrolyte for hydrogen electrooxidation and for solar fuel production. So I'll just walk you through a little bit of those applications and then get into some of the behavior of the material. Let me just point out that it is an incredibly abundant material, despite the fact that it is a rare earth element. So here is Ceria in terms of the abundance in the Earth's crust, and it is comparable to things that we don't think of as terribly rare, zinc and copper. Nickel, so on. Some of these are expensive, but not prohibitively rare. You wouldn't think of copper as a rare earth. So there are, 40 megatons or so worldwide reserve. So quite reasonable to use for large-scale energy applications. Again, sort of the examples from my laboratory, we've used it for catalysis, making these lovely inverse opals. This was in collaboration with Bruce Dunn at UCLA, where you use this material as a catalyst support. In this case, we were just demonstrating propane oxidation by controlling the architecture together with depositing various catalysts. Much more typical for my laboratory is to use it in a fuel cell application. This is the conductivity of the material as a function of oxygen partial pressure and various temperatures. We have an electrolytic regime when it is under reducing conditions, meaning a low oxygen partial pressure. The conductivity rises because it starts to go a little bit N-type because you start getting some of the 4+ cerium becoming 3+, gives very high conductivity. That contributes to its usefulness as a fuel cell electrolyte and a component in the fuel cell anode. And so from that, we get these record power densities. So these are 1 watt per meter squared in terms of power outputs at 600 degrees Celsius, which at that time was very much a record performance for a fuel cell achievement. Then in terms of solar fuel generation, the idea here is that we have our cerium dioxide, we heat it up to high temperatures, and as a consequence of heating it up, it releases some oxygen. We cool it back down, expose it to steam. It reacts with the steam in a way that reoxidizes the oxide and then releases hydrogen. And then we can do this cycle literally hundreds and hundreds of times, and we're able to produce fuel during each cycle. This is an example where we release the oxygen on heating, introduce the steam, and then produce the hydrogen sort of as expected. Did a demonstration with an actual solar furnace. This was a simulated sunlight, but still very close to what you would do in a real solar concentration scenario. And in this case, we were demonstrating CO production, where we were providing CO2 as the reactant gas. And then again, as a consequence of oxidizing the oxide, the released gas is now carbon monoxide, which becomes a component for making liquid fuels. So again, these are just the broad overviews of why cerium dioxide is important and interesting. So let me dive now into some of the science of what we've done here beyond the broad application sides. One of the things that's very important is the fact that in this particular material, the internal interfaces, the grain boundaries, are quite resistive. And that becomes a real challenge if you want to decrease the operating temperature of the fuel cell. So let me jump into that. And then the second part will be talking about the external surfaces, which of course matter for the catalytic applications that I've described. Here is an example of showing the influence of the grain boundaries in the bulk region of the electrolyte. What we've done here is create materials with different nanostructures, so different grain sizes, between 33 and 73 nanometers. And what you can see is that with the smaller sizes, the more nanostructuring, the larger the impedance overall. So the way that you read these impedance spectra is basically the magnitude here along the real axis is the equivalent to the DC resistance. And the larger the grain size, then the smaller that resistance is, basically because we have fewer interfaces to traverse. And the explanation for this generally has been that there's a region at the interfaces that is inherently positively charged because it has a slight excess of cations. That positive charge induces a depletion of the positively charged vacancies, which are the charge carriers. And because you've depleted those carriers, that causes the conductivity to decrease. So this has been the prevailing view in the literature, that there's something sort of a thermodynamic reality about these materials that inherently produces positive charge right at those interfaces. And this is also, by the way, associated with an increase in electronic conductivity, but oftentimes we don't observe that too much. What's really challenging is this decline in the vacancy concentration, and the oxygen vacancies are the carriers for the transport. So it's very important to know really what causes this, and is this really the explanation for this interfacial behavior? So what we wanted to do then was to see if we could directly detect that space charge region, confirm that it is the origin of the grain boundary impedance. What is then the origin of the space charge effect itself? Why are the grain boundaries positively charged? And then, I put out here the question, do impurities play a role? And I will tell you absolutely yes. And then we wanted to also understand, we do a macroscopic measurement. How much do the individual grain boundaries vary from one to the next? And can we use that in some way to manipulate the macroscopic properties? So what we've done, what I'll describe to you, is a study of lightly and nominally undoped Ceria. We have probed the interfacial charge by using electron holography. We studied the chemistry by using atom probe tomography. And then we do transport measurements across single grain boundaries by using bicrystals that we can then access those individual grain boundaries. One thing I'll say is that the reason that we've used lightly doped Ceria is because the width of the space charge region is inversely proportional to the square root of the dopant charge concentration. And so the smaller the dopant concentration, the larger the width of the grain bound of the space charge region, if it really is a space charge, and therefore it makes it easier for us to detect it. Here's our just a very typical material that we've started off with. As I said, very, very lightly doped, so 0.1%. And we center this so it has large grains so that we can access any one of these individual interfaces. And we're going to do that then by atom probe tomography, by electron holography. And atom probe tomography, actually. And what I want to point out here is this is an impedance measurement. And because this material is so lightly doped, the impedance is extremely high. And this little arc here is the bulk impedance. This large response here is the grain boundary impedance. We convert that to actual values of conductivity. And we can see here that the grain boundary impedance is extremely, extremely high. So a little bit of a challenge to measure this, but I'm going to show you now how this grain boundary value compares to the individual grains later on. Okay, so here we are going to use the electron holography now to see if we can detect a space charge potential at those interfaces. And the reason that the way that holography works is we take a beam, an electron beam. This is a coherent electron beam. Split it into two. We have our sample where part of the beam goes through the sample, part of it goes through vacuum. We recombine the two beams using this biprism crystal, and then we generate a hologram. So it's very much like any optical hologram you might have seen. And from this hologram, we reconstruct the, we do a Fourier transform to reconstruct the amplitude and the phase that was associated with the electron beam coming through the sample. And the phase really carries the information about the electric field that the electron beam traveled through as it went through the sample. Okay, so there's a lot of analysis here, and I have to really thank my collaborator at Argonne National Lab, Sidi Patak, and I had a really wonderful student who was doing this work. My pointer seems to be stuck. All right, so here's an example where we've taken an FIB cross-section, so focused ion beam slice out of our polycrystalline sample. Here's the grain boundary. We tilt it slightly away from the zone axis. Hard to see here, but this is the electron hologram. And right here is that grain boundary. We go in and zoom in. You can see the hologram has very good contrast, and that's what we're able to use to now reconstruct the phase information. And so here's the phase information again. It's you might think that it's that the grain boundary is not there. It's even hard to see the sample edge, but they really are there. Here's the amplitude reconstruction. And the reason we need the amplitude reconstruction is that we are recognizing that the electric potential is given by this phase value divided by the thickness of the sample, and the thickness of the sample is carried, that information is carried by the amplitude. So we use both of them to now reconstruct the electric potential profile. And this is a microscope instrument constant, which is known. So there's our phase reconstruction. Here's our thickness from the amplitude. And here is our reconstructed electric potential profile. And what you can see is that, so this rectangular region corresponds to this rectangular region. And indeed, there is a large value of the electric field just at that interface. And so we integrate that across this, let's call that the Y direction, and we get a profile that looks like here. And we can see that there is a potential right at that interface, which is close to 1 volt, which is really quite a large potential at the grain boundary. A couple of things that we have to correct for. One is that the electron beam may not be exactly parallel to the grain boundary. The second is that there is a little bit of leakage of the electric field into the vacuum, which would overestimate the potential. This one would cause us to underestimate the potential. So we do corrections for those two. And then we, as I said, look at many, many different interfaces. And what we can see is there is indeed a wide range of the space charge potential. That's the value right at the interface. So that's the peak value of that voltage. And it spans from over 1 volt down. In some cases, we saw interfaces that had no voltage associated with them at all. It's quite a remarkable range. And we can also, from our macroscopic conductivity or impedance measurement, compute an average, what we expect that space charge potential to be, which is really relatively small, about 0.4 volts. The way that that is calculated is to use this expression here. It's a derived expression. And the other implication of this relationship is that here's the space charge potential. It tells us that, in fact, there would be many orders of magnitude of variation in transport across each one of these individual grain boundaries. So, whenever you look at a small enough scale, you see variations. And here, this variation would be orders of magnitude. And it tells us that the transport really must avoid some of those high impedance interfaces and travel along the more conductive grain boundaries. All right, so this is the range in interface potentials. Now, we wanted to understand, as I said, whether or not there was any contribution possibly from impurities at those interfaces. When we did that electron holography, we also did electron microscopy, chemical analysis, and we could not detect any impurities. In fact, we couldn't even detect our dopant, which was there at the level of 0.1%. However, atom probe tomography is more sensitive even to the chemical analysis, to the presence of impurities. And this is a technique where you create this very sharp tip from the sample and pull off individual ions using a large electric field, and then detect what emerges at an image plate here. It's about 50% collection efficiency. So almost every single atom that is in the sample is detected. And by keeping track of the time of flight and the angle of each one of those ions, we can reconstruct what must have been the chemical distribution of atoms within this sample tip. Now, you have to be very good. Again, my student was very good at this, to be able to cut this pin and be able to actually have a grain boundary within this sharp needle region. And what we see, here's an example of one. Here's before running the atom probe tomography, and here now we've lost that top sample of material. So we're probing this amount here. And let me see if I can get it to show the movie. So that's our interface in there. And it has a number of impurity elements, and I'll describe to you what they are, but they are quite detectable in the atom probe tomography, whereas we were not able to detect them with the right in the electron microscope using the chemical analysis, the EDS methods. So here's the concentration that we see. These are just two different examples. And the most prominent impurity is aluminum. And the next one is, our dopant is enhanced at the interface. This is kind of a known phenomena here, that the dopants tend to go into the interface into the grain boundary region. The next impurities are calcium and silicon and some other rare earths, which really don't impact the properties overall. What's important is that the aluminum and silicon are quite sharply placed at the interface, and these are very strongly positive charged elements. At the interface, again, this is the enhancement of the samarium dopant, and these are the impurities, the dominant impurities in the system. Now, what we've done is say, let's imagine then that the aluminum and silicon are truly just at the interface, and that the oxygen that charge balances them goes further out into the bulk of the material. And from that, we can analyze the behavior. And let me just say that the overall bulk average impurity concentrations here of 18 and 5 parts per million of aluminum and silicon respectively. This is incredibly pure sample. So sometimes I show this and I feel like the audience says, wow, you just made an impure sample. Well, this is incredibly pure. It would be, let's say, technologically and cost prohibitive to try to make samples that are purer than this. What we're detecting are the impurities right at the interface. So even at this very low impurity concentration, we have high concentrations at the interface because these species are incredibly insoluble in the Ceria. So now we're going to use these concentrations to compute the charge density, again, making an assumption about the valence state of these impurity ions and an assumption that the oxygen vacancies, or the oxygen ions that provide the charge balance, are in the space charge region as opposed to being right at the interface. And from that, we can compute out also the space charge potential. And so this is the result that we get from these two interfaces. We see in one case a voltage of around 1.3 volts at the right at the core, 0.6 volts. This one is lower largely because we have calcium, which is a substitutional dopant, which shields or against these impurity concentrations, not because the impurity concentrations are low. And this hints to us actually a strategy for avoiding these effects as opposed to trying to have higher purity, then it strikes, it immediately promotes the idea of using counterdopants to diminish this interfacial charge. Okay, so we have a lot of sort of circumstantial evidence now. These were two different systems. Let me go back. When I say two different systems, I mean, this is one set of grains, and the electron holography that we did was another set of grain boundaries. So there are two different grain boundaries. We weren't able to do the holography and the tomography on the exact same grain boundary. So this is, in that sense, a little bit circumstantial that would suggest that the origin of the charge is these impurities. What we then did was say, let's come up with a way to do multiple measurements on a single interface, on a single bicrystal system. And we created this platform for measuring bicrystal samples where we could do the electrical measurements by AC impedance and also by DC methods, that we could look at the grain-to-grain orientation using electron backscatter diffraction, and that we could look at the chemical impurities here, if there are any, using secondary ion mass spectrometry, which is not as quantitative as atom probe tomography, but certainly gives us an important qualitative signature of whether or not there are impurities present. And we were fortunate that we could get some commercial nominally undoped Ceria fibers that have the optimal configuration, optimal geometry for us to be able to have these grain boundaries that are normal to the length of the fiber. We have this nominal impurity concentrations. These are, of course, much higher than the impurities that in our high purity sample. This is what are given to us from the manufacturer. And we can see that the interface here is certainly, despite the presence of impurities, is a sharp interface with no impurity phase per se. It's just impurity concentrations. Okay. All right. So now let's look at these interfaces. First thing that we did was just measure a crystal without any interface, make sure that our apparatus was working well, and we can measure these very high impedances. We compare the conductivity that we measure here with a polycrystalline material that we make out of this fibers, make sure, again, everything is self-consistent. And then we measure the bicrystal with an individual grain boundary at the interface. And what we see in our DC measurement is that there's a huge impact of having this interface. This is the measurement of that single crystal, this one right here, and then 6 bicrystal samples where you can see that the current is much lower, and it's also now nonlinear compared to what it was with the single crystal. And that is consistent with a space charge effect where it's not an ohmic response, but again, this nonlinear response in the linear sweep voltammetry. And using the electron backscatter diffraction, we are probing here the grain-to-grain orientation. This is a little bit like an Escher picture, a little bit hard to see. This is the underneath part of this crystal. So this is the platform on which it's sort of supported down here. This is the bicrystal sort of floating. These are the orientations now of the two different crystals. We can get the orientational relationship between the two of them. And underneath here is the magnesium oxide support that this whole platform is sitting on. So that's the red region. The key is that we can see these two different crystals that make up this bicrystal, and we can get their orientation relationship between the two of them. And then with the secondary ion mass spectrometry, the SIMS measurement, we can see again that we have aluminum enhancement right at that interface. So we've done this measurement now on these 6 different interfaces. And so let's summarize what we get from that. What we see is, once again, aluminum is our largest impurity that shows up. Silicon is dominant, and calcium is also dominant. So these are our 3 most important impurities species. Aluminum and silicon lead to high space charge potential from our calculations because they have high charge and they are not substitutional elements. They go right into the grain boundary. Calcium is a substitutional species and has lower charge. And so it tends to screen the space charge. And we can see now that if we compare the impurity concentrations to the conductivities, this is now resistivity, that the higher the impurity concentration, the higher the overall impedance across that interface. And we see also somewhat of a correlation with the nature of the crystallographic relationship between the two grains. When the two grains have a smaller angle misalignment, we have a lower impurity concentration and a lower overall impedance. And from a thermodynamic perspective, it makes sense that if you have an interface which has a low surface energy because it is a nicely aligned interface, then there's a less of a thermodynamic driving force to for the impurities to be trapped there. And so that gives you a low impurity concentration and therefore a low impedance across that interface. So all of these things are correlated, and now we can understand what the origin of the space charge effect is. But really it is about these high valence impurity species that end up at interfaces which are have a high crystallographic misalignment associated with them. So that is our story now on the internal interfaces, that we have these grain boundary potentials, which we've confirmed that they really are there, had not been done before in the literature. There was a lot of circumstantial conclusion that they occur. We see that it's largely due to trace impurities. There's this immense variation from boundary to boundary, and this impurity concentration is correlated to the nature of the crystallographic relationship between the two grains. And that means that in terms of the future strategy, we want to modify the chemistry in terms of adding species like calcium to mitigate the charge rather than trying to purify further beyond 10 ppm. That, as I said, is cost prohibitive. So that's, again, our story on the internal interfaces. Now let me move to the external interfaces and what this means in terms of surface reaction rates and how that's connected to the extent of reduction at the surface. All right. In this case, we're going to be studying Ceria zirconia as opposed to rare earth dope Ceria, because this is a material that's been used very much as a catalyst support. So the bulk properties of the Ceria zirconia, here's the phase diagram of this material. Ceria by itself is a cubic fluorite structure material. The zirconia is a distortion of that. At room temperature, it's monoclinic, higher temperature tetragonal, and then at the very highest temperature, it's cubic. Typically, we process the material at around 1500 degrees Celsius and quench from here. So, and we keep our zirconium concentration in this range, and we are therefore looking generally at cubic materials in our experiments that I'll describe. One thing that we can see is that the if we look at the amount of oxygen per unit cell as a function of the amount of zirconium that we've introduced into the material, here is that oxygen content. The more zirconium is in the material, the less oxygen there is, which is kind of a surprising statement. It's saying that the material is reduced when we introduce zirconium. For a chemist, you know that zirconium likes to be strictly 4+. Cerium is the one that goes between 4+ and 3+. Zirconium stays strictly 4+. So why would we have more oxygen vacancies, which are associated with having 3+ cations when we introduce zirconium? So, and we see that's true regardless of temperature. So this is 800 C, this is 1500 degrees Celsius. We can convert this into a thermodynamic statement, which is to say that the enthalpy of reduction gets larger in magnitude the more the cerium concentration is. So somehow introducing zirconium reduces the thermodynamic penalty of having oxygen vacancies. And if we go back to the crystal structure itself and the crystal chemistry, what we speculate is happening here is that we have this material which has the fluorite crystal structure. The cations in this system are 8-fold coordinated. Cerium is a large cation, whether it's 3+ or 4+, it's even larger when it's 3+, and it's very comfortable having 8-fold coordination of oxygen ions around it. Zirconium, on the other hand, is not comfortable with 8-fold coordination. In fact, that's why at room temperature it distorts away from the cubic phase to the monoclinic phase. And it wants to have only 7-fold coordination. And I love thermodynamics because it allows us to give anthropomorphic qualities to inanimate objects. So zirconium wants to only have 7-fold coordination. It can kick out an oxygen ion as long as the cerium agrees to adopt the 3+ coordination oxidation state. And so there's a synergistic effect between the two, which allows the material to be more reduced when we introduce zirconium, despite the fact that the zirconium remains in the 4+ oxidation state. Okay. All right, great. That would tell us that oxygen vacancies are likely to be close to the zirconium as opposed to being randomly distributed as they are when we would introduce, for example, a rare earth dopant, which is a 3+ species. Right. So now Ceria, as I said, is used very much as a catalyst support and as a catalyst itself. And there's a lot of interest in the surface chemistry. The different terminations here have been studied in terms of predicting both the surface energy as well as the vacancy formation energy. So the surface energy is lowest for the 111 phase, so you'd expect that to be most stable. The vacancy formation energy is computed to be lowest on the 110 phase, so one would expect this to be most effective. And we expect that oxygen vacancies on the surface would somehow facilitate catalysis. And as a consequence of that expectation, there is a lot of interest in doing what's called shape selective synthesis of Ceria to be able to create, in particular, this kind of structure, which has a lot of the, 110 or 011 phase that should catalyze a lot of reactions or have high catalytic rates. Here's an example from Overvee's lab from several years ago, where you have this, a lot of 011 termination, a lot of 001 termination, and then a lot of 111 termination. And the example in this particular study was to look at CO oxidation, look at the rate of that. And what was observed was that indeed the rods with the lot of 110 termination were the most active than the 100, with the intermediate concentration of oxygen vacancies, at least computationally expected, moved up in terms of activity. And then the lowest was the 111, which had the nominally the lowest oxygen vacancy concentration. So this looked like an open shut case that the explanation was there. But I will tell you that if you look a little bit further in the literature, this trend is not always obeyed. And so it's not clear that this is a universal response. And it's also not clear, there's not been much of an attempt to directly measure the vacancy concentrations on these different surfaces. There have been a few here, and it is well known that the surfaces of Ceria have higher vacancy concentrations than the bulk. What's not clear is how the different terminations vary. And these are just examples in the literature showing that indeed, for example, there's more cerium 3+ on the surface than there is 4+ on that surface compared to the bulk. If you make the particles small, the lattice parameter increases, and that's attributed to having more and more cerium 3+ because you have more surface area. So a lot of body of evidence that says the surface is more reduced, but again, not really a comparison of different terminations and understanding what that means for the catalysis. This is just another example by XPS, which is a very challenging method to do this measurement because you have to do differential pumping. Similarly, with the electron microscopies, this is all either under vacuum or with differential pumping so that you can keep the instrument electron detection under vacuum while the sample itself may not need to be under vacuum. But these are very challenging experiments. And so we wanted to go and really answer this question in a way with a little easier approach. So the questions are, we know that zirconium doping increases the bulk vacancy concentration. Does that mean that it also increases the surface vacancy concentration? Because that would be great if the catalysis is really associated with the vacancies on the surface and zirconium gives us more vacancies on the surface, then it should be a great catalyst support and a great catalyst itself. And so that's what we were going after. The other question is this difference in orientations. Is there really a difference in the vacancy concentration on the different facets of Ceria? So as I said, we're going to try to do the measurement with a somewhat easier technique than these vacuum methods. And the measurement of the oxidation state we're doing by X-ray absorption spectroscopy. We can probe both the surface and the bulk concentration using this method. And we're going to measure the reaction rates and also get the bulk diffusivity by a technique called electrical conductivity relaxation. So let me introduce that macroscopic measurement first. The way that we do this measurement is to do a straightforward, let's call it a 4-probe conductivity measurement. And the overall idea is that if we can change the oxygen concentration in the gas phase in a very sharp and brief way, that we will see a change in conductivity that reflects that change in gas phase oxygen concentration. And the conductivity will relax to a new value. And if we track this relaxation rate, then we are able to extract out kinetic information about our material. So I like to say that, we have a very relaxed lab. We do a lot of relaxation experiments. So again, the idea is we do a step change in oxygen partial pressure in our chamber. That introduces a change in the vacancy concentration in the bulk material as either it gets oxidized or reduced. And therefore, that changes the conductivity, and we track the rate at which that conductivity changes. It gives us information both on the diffusion coefficient as well as the surface reaction rate constant, because both of these control the rate at which the material relaxes to having the new vacancy concentration. Okay, so we've got a diffusion coefficient that reflects neutral oxygen diffusion through the material, and then a surface reaction rate constant that reflects this oxidation or reduction of the material. Okay. All right. And of course, we need to have a material that changes its conductivity with changes in oxygen partial pressure. And so we see that here, and we're studying 15% zirconium doped Ceria. And we've just have two different ranges that we can access given the gas compositions that we're using. And so we're going to now do step changes within these individual regions. So we do a step change where we change the oxygen partial pressure to such a small amount that you wouldn't be able to see it within the size of this dot. And the normalized change in conductivity looks like that. We change the gas flow rate just to make sure we're actually measuring our sample and not the chamber, for example. And we can see these all line up. Great. Let's do an example here. And this is just to show you that the forward and reverse are also the same in this normalized conductivity plot. That's important because we're assuming a linear response. So we need the forward and reverse to be the same. Again, tells us that our step change is small enough. Okay, so now from this, we're going to extract our kinetic parameters. Well, just coincidentally, we are using a sample thickness, which is 0.75 millimeters in thickness, and that turns out to give us a response, which is dominated by diffusion and this higher oxygen partial pressure regime, and then one that's dominated by the surface reaction step at this lower rate, which is to say that the surface catalysis is slow, and therefore we can't access the diffusion coefficient, and conversely for the other case. Now, what we can do is we can add a catalyst to speed up the surface reaction rate here so that we can measure the bulk diffusion in this case. So in this case, we can get the bulk diffusion and the inherent surface reactivity constant. In this case, we can get only the diffusion coefficient. Okay. And it just has to do with the thickness of the sample that we use for this experiment. The most important thing is to show you that introducing zirconium, despite the fact that it has all these vacancies that it creates for us, causes the diffusion coefficient to go down. This is an earlier measurement that we had for Ceria, a dramatic decrease, an order of magnitude decrease in the diffusion coefficient. And going back to why that might be, I hinted at it earlier that the oxygen vacancy is evidently trapped at this next to the zirconium ion. And if we look at the surface reaction rate constants, it's a similar story. In this case, again, decreased by more than an order of magnitude, and surprisingly, a very weak temperature dependence here. So that was quite surprising to us. Let's see, now my cursor is stuck. Let's see what's going on. Okay. So now we are going to now connect to that surface redox chemistry, which I said, okay, all of this is, macroscopic a little bit here. Zirconium, which we know introduces vacancies into the bulk, causes the surface reaction rate constant to decline. Let's see if we can understand, make a connection to the vacancy concentrations that we can measure by more direct methods. And the method that we're using, as I said, is X-ray absorption spectroscopy. We're using the near edge region here, which gives us the cerium oxidation state. The extended region gives us the coordination number. It's much harder to model. With the Zane's region, we're really looking at whether we have cerium 3+, which is given by this red spectrum, or we have cerium 4+, which is given by this black spectrum. And I just put this out here because this is an electronic structure conference to say that this is a really, unfortunately, complicated spectrum for the cerium 4+. Not my measurement at all. This was calculated some years back, but it's important for us to be able to understand what this fully oxidized cerium 4+ spectrum looks like so that we can use it to calibrate our own measurements. Now, what we're doing with the Zane study is grow thin film of Ceria and change the incident X-ray angle that we're delivering the X-rays at, because if we're at a very shallow angle, then we are below the total internal reflection, and we get very small signal, weak signal, but that signal is entirely from the surface. When we're at a large angle, and we typically do it around 8 to 10 degrees, then we are probing the entire bulk. So we're going to be either skimming the surface at this very shallow angle of around 0.2 degrees, or we're going to be at a large angle where we can detect the entire film, and the film is around 220 nanometers in thickness. And because this is an X-ray measurement, we can do it in situ, meaning that we can go to high temperature, we can control the environment, introduce oxygen, introduce hydrogen to make it more reducing, and we can also do fluorescence at the same time so that we can measure the cation chemistry, and we can get the single crystals in different orientations so that when we grow our Ceria film on top, we get different terminations of the Ceria film. Okay, and so we can do both the surface and the bulk. So it's just a beautiful measurement. We can get everything we want. The one thing that we can't detect absolutely is to know whether or not the vacancy concentration tracks with the cerium 3+ concentration. Because what we're getting from this measurement is the serum 3+ concentration, not directly the vacancy concentration. And we're going to make the assumption that the two are charge balancing each other, and there's nothing else on the surface. This is a high enough temperature, most of our measurements, that there's nothing at the surface which is providing some charge balance. At a lower temperature, you might expect some hydroxyl groups or something like that to be on the surface in a way that can provide the charge balance, and then these two would be out of alignment from each other. All right, so just quickly then, the materials that we've made some uniform composition ceria, usually on yttria-stabilized zirconia substrates, and we've done 3 different orientations. And just to make sure that there's nothing, an influence from the substrate, we've done one example on our sapphire, which is alumina. We also did a compositionally graded film so that we could quickly measure the influence of zirconium. And get lots of different compositions essentially in one fell swoop. In the era of big data, this is becoming more and more important. So we do a compositionally graded film, ceria at one end, zirconia at the other end, and then we pattern it so that we know where we are when we do the Zanes measurement across here. We got 19 strips, but time on the synchrotron, we only measured maybe about 9 or 10 of them. Okay, so one thing that we want to make sure, because we're looking at the surface, is that there's no composition gradient between the bottom to the top of the film with respect to the zirconium concentration. And this is the top part of the film. This is the bottom part of the film. We're doing X-ray fluorescence as a function of penetration depth by changing the incident angle again. And we can see that there's no, statistically significant variation in the zirconium concentration as we go through the thickness of the film. So that's not going to be a cause of any difference on the surface compared to the bulk. And we see that in our graded composition film, the material maintains its orientation as we change the zirconium concentration and systematic change in the lattice constant, as you expect as you introduce more and more zirconium. So all of that looks good. And here's our Zanes result. The most important point here. You can see that in this particular measurement, this is for a 4.25% doped zirconium, high temperature, very reducing conditions. We can see that the surface looks much, much more like that cerium 3+ reference spectrum that I showed you compared to the bulk. The bulk looks very much like that 4+ reference spectrum. And we do the analysis by linear combination fitting so that we can quantify the cerium 3+ concentration. And you can see here, it's about an order of magnitude difference in terms of the extent of reduction at the surface versus the bulk. So the surface is far, far more reduced than the bulk. That we sort of knew going into this, but how about the influence of zirconium concentration? Well, this came as a real surprise because there is none. Basically, the zirconium, despite the fact that it makes the bulk much, much more reduced, it doesn't make the surface any more reduced. And in fact, this measurement we did on a separate day, and I suspect that we didn't have the same control on the gas atmosphere as we did here. And that's the reason that this is a bit of an outlier compared to the others. So the zirconium has really no impact on the surface cerium 3+ concentration. And we've sort of validated our experiment overall by showing here that the measurement that we get by Zanes in the bulk is the same as we get from the thermogravimetric analysis, is what I showed you very early on when I introduced this topic. So those two match up. So they're we validated our Zanes measurement, and we can see now that indeed the surface is far more reduced than the bulk, and it doesn't depend on the zirconium concentration. Kind of a surprise. Now, as we go to the case of a far less reducing condition, in fact, just the air condition, and we measure it at 3 different temperatures. Here is another huge surprise. First of all, we can see that the cerium 3+ concentration, in fact, declines with increasing zirconium concentration. This is exact opposite of the bulk. Despite the fact that the surface is more reduced than the bulk, because the bulk has no reduction at all under these conditions. But the trend with zirconium concentration is counter. The surface reduction extent is now insensitive to temperature. So these are, quite different in temperature values, but they're, all the same reduction extent. That's true under air, which was not true under hydrogen, which was the previous slide. And this looks a lot like our surface reaction rate dependence. This is also under moderately oxidizing conditions. And we saw that there was not much temperature dependence at all here. So this 900, 850, and 800 look almost the same. Here, of course, we have a much wider temperature range, but it just doesn't seem to be surface sensitive, which is quite anomalous. Now, the last piece is the difference in terminations. And here we have 3 different terminations measured. And you can't even see the difference in the data points. They fall right on top of each other. This is at high temperature under air, high temperature under nominally reducing conditions. And this is just one of the measurements of the 001 orientation that we did under even more reducing conditions. They look exactly the same, initial, final. So we know there's no evolution of the sample over the course of the measurements. So this is a real surprise. I view that there's a knot here in terms of understanding what's happening with the surface of Ceria. We're starting to unravel this knot, that it is not a simple relationship between the vacancy concentration on the surface and the catalytic activity. Certainly, there's no simple relationship between the vacancy concentration on the surface and the termination, as was predicted. What we see on the external surface is that the surface is far more reduced than the bulk. That's consistent with predictions, but it's very either independent of zirconium content or declines with zirconium content, the opposite of what one expects. The kinetic parameters are penalized when we introduce zirconium, and we speculate that's because the vacancies are immobile. The reason that there are more vacancies is because zirconium wants to have a lower number coordination shell. And so those vacancies are stuck there right next to this zirconium. And again, the extent of surface reduction appears independent of termination. And so there must be other reasons why these different size controlled catalyst particles have difference in catalytic activity. Okay, so with that, let me thank the 2 students who did most of this work, Shinshu, who did the first part on the interfacial materials, and then Weizi Yuan, who did the second part on the Zane's measurements of the surfaces. My collaborators who were really phenomenal here in making this work, and funding from NSF and through Argonne ISIN. We went through our period of having our group meetings through Zoom like everyone else did. I'm very happy that we're back now in person. And I want to thank you for your attention. And I will put this sort of summary of what I've told you up here to help guide any questions. And thank you for your attention.
Thank you, Sossina. I am Michel Côté from the University of Montreal. I'm stepping in for Omololu, who seems to have internet connections problems. Okay. So I would just manage the Q&A questions. But thank you for your nice presentations. So now the session is open for questions. So please raise your hand so that I can give you the rights to speak. I might just kick off this with a question for you. Can you tell us how electronic structure calculation can help you further in your investigation? You did mention that there's this EXP spectrum that can be calculated, but is there other way that you think that electronic structure can help?
Yeah, I mean, I would say that part is actually still open. And what I didn't tell you is that, so we do our Zane's measurement, and we basically analyze the spectrum by doing the linear combination fitting, which is, gives us big error bars, big uncertainties, and you get the overall shape of the spectrum. What we did notice between the 3 different orientations was that the intensities were slightly different. And I've heard it be argued that reflects a level of covalency in the bonding, even though the oxidation state might be, sort of globally the same. And so that's still a point of interest for me. And certainly the electronic transport, these are in the zirconium dope system, it's very much an electronic conductor as opposed to an oxygen ion conductor. We've been trying to sort out through our macroscopic measurements, the magnitude of that, when it's N-type, when it's P-type. So there are a lot of questions there still.
Okay, great. So let's hear David's questions.
Hey, thanks very much, Sossina. Really nice talk. Just to follow up on this discussion about the importance of electronic structure, I think it's really important to emphasize for the folks listening here too that this ability for cerium to change its oxidation state back and forth, depending on the dopant concentration or the local oxygen vacancy concentration, is actually very interesting as well from an electronic structure point of view, purely, not even just thinking about the X-ray spectroscopy. It's an interesting catalytic system to think about, because we've studied this in a different context and noticed that you can dope your surface with atoms like platinum or others. There's lots of single atom catalysts that can be supported on Ceria. And those single atoms have this ability to alter their oxidation state, because anytime they want, they can exchange electrons with the substrate. And it will absorb them quite easily. So you can start with platinum as a dopant, as a substitute, let's say in 4+. Next to a vacancy, it becomes 2+, which means it eats 2 cerium polarons. And then as you do your reactions, it goes back and forth between 2+, 3+, 4+, all the while sometimes exchanging with the Ceria, sometimes not. And so it's a really fascinating system from an electronic structure point of view to understand that catalysis could have this local, almost electrochemical component to it as the system evolves. So that, I think that's intellectually very interesting from my point of view. I fully agree. Yeah, I was curious about do you have evidence for the zirconium concentration variations as a function of depth? Is there any change? That was the let's quickly go back. That was within the fluorescence measurement. No, I mean this is the depth profile. Okay, got it. So it's pretty constant. Yeah. So this is 3 nanometers. So you could argue and say maybe very top surface, maybe it's different, but across this we don't see anything. Okay. Yeah. And then, the only other thing you mentioned briefly was that there might be hydroxide at the surface as kind of a reservoir of charge to stabilize things. Right. At the lower temperature, at 800 C, that's not extremely unlikely, because it'll just desorb at those temperatures. Yeah. Okay. All right. Anyway, thank you for permitting the comment. Anyway, I'm also equally interested, I think, in this material, and very enjoyed the talk. Yeah, really nice. Thank you. Yeah. Thanks. So, just to follow up. Oh, go ahead.
Well, there's another question from Shanae, but maybe you want to follow up on David's questions first.
I was just going to say that even as you put metal catalyst particles on the Ceria, you do change the cerium oxidation state. I was just saying that we had also observed that, and many have observed it in literature. It's very true. But, okay, go on.
Shanae, can you want to ask your questions?
Yes, hi. Thanks, Sossina. I was just wondering, since a lot of this is driven by this coordination, kind of this competition between the 8-fold versus 7-fold coordination that the zirconium allows, would there be a way of doing or controlling these effects with like strain or substrate templating that will allow you to kind of sterically control this?
Yeah, that's a good idea. We haven't explored that. There are folks who've tried to use strain on films to change the catalytic activity, change the oxidation state, change the ionic conductivity. That's been a big effort. We haven't pursued that ourselves, largely because we were going after this idea of what does the shape selective particles do for the catalysis? Is that really the question? And there, of course, they're not controlled. But I do think there's a lot of opportunity there. Yeah. I'm trying to think if we have any example from that. So our films we intentionally made them thick enough that all the strain would be gone. I do know that there, actually my former student who did our XPS measurements that I showed you here, he's done very, very thin films where they are strained and seen a big difference in terms of the oxidation state. Yeah.
Maybe someone here wants to do the calculations. Anyone is interested? No. Okay.
Yeah.
Thanks,
Let me ask a question that was posted on the chat by Omololu. He was wondering about the number of grain boundary as it might be reduced when annealed. So at the beginning of your presentation, you did mention the grain, this dependence on the size of the grain, but if you anneal, what's happened? You can
right. So that's how we change the number of density of those grain boundaries, is by sintering at different temperatures. So Ceria is a relatively inert material in terms of the cation motion. So you do have to go to high temperature to change that, the grain size. When you're starting off with very fine particles, then you can you have a range because you have a high surface energy total that drives the system to have larger grains. But once you get beyond maybe 2 microns, then it gets harder and harder. You have to go to higher and higher temperature to get the grain size larger. But that's essentially what we did. And you could see that as the grain size was small, even though it was 33 nanometers or so, and people are all excited about, nano effects, it was linear with the number of grain boundaries that you have to traverse. And so a completely trivial grain boundary effect in the sense of it's completely expected. The more grain boundaries you have, the higher the total impedance that you get from those. And they're basically all the same individually. Now, what can happen is if you grow the grains, sometimes you get a higher impurity concentration per grain boundary because you have a total impurity concentration in your sample. So each one individually can become more resistive as a consequence of the grain size going up. But that's, when you go to extreme changes between small and large.
Okay. Thank you. So I don't see any more questions. So let's thank the speaker for the interesting talk. But before we do so, and if it's available to you, open your camera so that our speaker can see some real face in this time.
Yeah, and that means I need to stop my share.
Thank you for your presentation.
Okay, thank you. Have a good enjoy the rest of the meeting. Thank you. Bye-bye.
Thank you. So I will leave the microphone to the next chair, Andres. I'm not sure if he.
I'm here. Thank you very much.
Okay, thanks.
Thanks, Michelle. So good morning, everyone. Again. And thanks to everyone for being here. It is my honor and pleasure to present the next speaker, Justine Etindele. She will talk to us about practical treatment singlet oxygen toward a C60 scavenging mechanism of radical oxygen species. Anne, can you share your screen?
Very much, Andres. Okay, let me share my screen.
There we go. Great. Thank you.
Okay, I hope you see it.
Yep, the floor is yours.
Okay, let me put it in. Okay. Okay, thank you very much for the privilege and the opportunity to be one of the presenters of this on practical treatment of singlet oxygen toward C60 scavenging of mechanism. C60 scavenging mechanism of ROS. For 2 weeks now, I've been working in the Cisneros group in University of Texas at Dallas. The presentation I'm about to do is focus on these 5 main points. I'll first give a brief comment on Cameroon, where I come from, and then I will focus on that practical treatment of singlet oxygen. And then I'll give some few steps of the project we have been doing in Cisneros group up to now. So I come from Cameroon. Cameroon is a country of Central Africa with more than 26 million people. And those people are divided in 3 main groups. The Bantu, semi-Bantu, and the Sudanic in the north. So it's pretty hot. That's why our traditional dresses are very light. And we speak 2 official languages, French and English. There are a lot of good places to visit and to love, of course, like the Bamoun Kingdom in Fumban and Yaoundé City, our capital. So, and there are many other places that you can visit. It's a very nice country. So Cameroon has 8 state universities, among which Bamenda, Yaoundé University, where I work, in the Higher Teachers Training College. And in that school, my office is in a laboratory where I have the opportunity to work with research students on 2 main areas, solid state and particularly 2D transitional metal decalcogenoid, and in molecular physics on scavenging properties of C60. And concerning that domain, we started a project with 1 PhD student, Abraham Ponha, in collaboration with Mark Asida, that many of you know, under the supervision of Motapon Ousmanu. So we started studying the scavenging properties of fluorine C60. And in the part of that project, I'm about to present you some general concept surrounding that project. And I'll show you that it's not enough to set the multiplicity of the singlet oxygen to be equal to the unity. And I will define the method we use to handle that state of molecular oxygen. I will also give you a few about some concepts like spin free, spin symmetry breaking, and spin sparing. Okay, let us start by saying that C60 belongs to a family of fullerenes that are allotrope of carbon like diamond and graphite. It has 60 quasi-sp2 carbon atoms, all equivalent. And it is very famous because it's predicted to be a good candidate for technological application like improvement of solar cell. And sometimes it's called panacea for its antioxidant properties. That is, it can help to cure so many diseases. Before defining antioxidant, let us start by defining free radicals. So free radicals are atoms or molecules desperately in need of electron to be saturated, for it has unpaired electron. So the molecule that can provide those needed electron or even protons to stabilize those free radicals are called antioxidant. But that molecule should not become a free radical itself after that. So this is an example of a free radical oxygen molecule with the 2 unpaired electrons. So it is desperately in need of 2 electrons to be stabilized. So that molecular oxygen is supposed to be very reactive, since in the atmosphere, we have up to 20% of the molecular oxygen. It's surprising that we are not just subject to instantaneous combustion. So that is because it is not really reactive as it's supposed to be. However, the two first excited states, the singlet, are proven to be very reactive. So that leads us to a difference between free radical and reactive oxygen species. So one molecule can be a free radical and not really be reactive, and another can be even saturated and be very reactive. This is a set of some reactive oxygen species, ROS, among which we have the molecular oxygen, which is in its singlet state. And we have also peroxide and hydroxyl radical. So if we go back to molecular oxygen, here represent the three lower states of the molecular, the ground state. Here, that is a triplet state. The first excited state, a singlet delta state, and the second excited state, the singlet sigma state. That can be represented like a sum of multiplet. Multiplet is just a combination of electron in molecular orbitals. So one can obviously see that these states are a combination of multiplet, and since DFT code is basically a single determinant code, it can hardly describe that kind of combination. So how can we handle the description of the combination of possibilities with just a singlet determinant DFT calculation? So there is a freely downloadable and personal computer compatible code named the density of Montreal, which can help to handle the combination of multiplets. So in the input of that code, we can specify exactly where we put electron in molecular orbitals. And so if we specify it, we can calculate the energy of that multiplet and then do the combination to have the energy of the states. So here is the principle of the multiplet sum method, the combination of the combination of energy of many multiplets. If we apply it, we will find the potential energy curve of the ground state, oxygen molecule ground state here in dashed line. That we compare to the experimental value from American National Institute on Standard and Technology data. And we have shifted the potential energy curve from twice the energy of oxygen. And here is the bit relief, it's done at bit relief and bit leap level. So we can realize that the dissociation of the two atoms is not correctly reproduced here. That suggests that we should take into account the symmetry breaking at a certain distance. So that symmetric breaking is basically attributed to the change in the value of the expectation value of the x square operator. That is supposed to be equal to 2 for the triplet state at around 3.7 that value changes, that is the distance at which we should consider the symmetry breaking. Okay, so just to explain what is the symmetry breaking, if we remember that the hydrogen molecule at the equilibrium position has its 2 electron paired, and when atoms move from one another, there is a spin flip occurring, and we might think that that kind of phenomenon should happen in molecular oxygen, and we can calculate the energy of the spin flip by this relation. And another phenomenon can happen, the 2 electrons can still remain on parallel. So the spin pairing energy can be calculated by this formula. So if we remember the expression of the energy of delta, singlet delta state and singlet sigma state, the spin flip and the spin pairing energy are related to those energy of those, the energy of those states by this relationship. So if we apply the multiplet sum method and we consider the spin symmetry breaking at many levels using density functional approximation like BLIP, we will realize that at that level, we are not able to well reproduce the symmetry breaking. But if we use an M06, that is a meta-GGA approximation, we can be able to reproduce in a pretty good way the potential energy of the 3 lowest states of molecular oxygen. So all these results have been published in a recent paper last year. So as soon as we have described the free radical, the next step is describing the interaction between the free radical and the scavenger. So for more than 2 weeks before coming here in Dallas, and in 2 weeks now, we have been working on not only looking at the interaction between the free radical and the scavenger, but we also consider the influence of environment in the Cisneros group here in Dallas. So what we do is doing molecular dynamic simulation, and then using a quadratic string model, we simulate the reaction between C60 and the free radical in a solvent, and later we will add on the cell membrane. So for that we use a code written by the Cisneros group, which is LIChem, which is an interface of quantum mechanic wrappers and molecular mechanics wrappers. And we do our simulation on an HPC under the portal of XCD, and the calculator is X10PD. So apart from doing, apart from working on that huge theoretical background on the codes, we have great time. We are having great time in the Cisneros group, thanks to Andrés Cisneros. So I want to thank the USAfrI initiative organizer I also want to thank the American Physics Society for the funds that allowed me not only to participate to that conference, but also to come here in Dallas. I want to thank, of course, Andrés Cisneros. I want to thank Columbia University and East African Institute of Fundamental Research. Thank you very much.
Thank you very much, Anne, for the nice talk. Are there questions from the audience? Okay, I don't see. Oh, yeah, Michelle. Go ahead.
Thank you for the nice presentation. And I'm happy to see actually that a code that started in Montreal is still being used. Mark Cassida started this programming this code when he was at University of Montreal, so I'm glad to see that. But can you explain what's the role of C60 as a scavenger? I mean, will it be the role as an antioxidant in this reaction, so it will make it reduce the free radical, or what's its role?
Okay. So as a scavenger, it will fix the free radical, like molecular oxygen in triplets. It will just fix it on its surface, and then it will reduce the number of free radical in the media.
So will it absorb electron or like give away electrons on the systems?
Actually, since it has many double bonds, it can provide electron to the free radical, and by the we are also looking at how it reacts with Mark Cassida. Does it behave like electron donor or electron acceptor? It really depends on the number of the free radical it has already captured, and it depends. It can behave both like two, like electron acceptor and electron donor, but basically it will fix the free radical on its surface. Okay,
thank you.
Thank you. There is a question in the chat from the USAfri director asking the QM part of the QMMM will be a multi-reference method, not DFT, right? Which one of you are you thinking of using?
Let me read it once again. Be much. Okay, we use both the two. We use Gaussian, that is a DFT calculation. We use the Gaussian, which is DFT calculation, and we use Tinker, like an MM method. So we use DFT code at the beginning of the calculation, that is Gaussian, and then we can do our molecular dynamic simulation later.
Yeah, if I may jump in, yes, obviously this is a multi-reference problem, and the DFT is single determinant method. So there are approaches, some developed by Mark Cassida, with whom Professor Etindele is working, that can be applied with DFT, like spin flip DFT and some other stuff. But obviously, we would also explore something like a small CAS or something. Given the size of the system and the complications with QMMM is not trivial, but it's not beyond the realm of capabilities.
Mm-hmm.
Are there any other questions? Okay, well, if there are no other questions, let's thank Professor Etindele again for the very nice presentation. And the next two talks will be recorded, and then we will have the Q&A session afterward. The second talk of the session is by Asnake Haile, and the talk title is The Role of Nitrogen and Sulfur Dual Coordination of Cobalt and Cobalt N4 X sulfur X C single atom catalysts in the oxygen reduction reaction.
Hello, everyone. First of all, I would like to thank the organizations who sponsored this workshop and the coordinators for the workshop for letting me to present my research work. And also, I would like to thank Dr. Tim from Western Washington University for his interest to hosting me. My name is Asnake Haile from Assosa University, Assosa, Ethiopia. My presentation title is The Role of Nitrogen and Sulfur Dual Coordination of Cobalt in Cobalt Nitrogen Sulfur Single Atom Catalysts in the Oxygen Induction Reaction. This is my presentation outline. Our daily life activities are dependent on energy supplies, and the main energy sources are fossil fuel-based energy sources. As you can see in Figure 1, the global energy mix is dominated by fossil fuel-based energy sources. So when we use this type of energy sources extensively, greenhouse gases are emitted into the atmosphere. This consequently leads to climate change. So we need to have sustainable source of energy because the observed climate change should be mitigated, and fossil fuels are now being depleted. Sooner or later, we will run out of fossil fuel. So we need to have alternative source of the best alternative to fossil fuel. Storing energy. Why energy storage? Because renewable source of energies are intermittent in nature. That means the sun does not shine all the time, and also the wind doesn't blow anytime. So we need to have energy storage or energy carrier system. So in this regard, hydrogen energy is one such sustainable energy carrier, and hydrogen energy systems appear to provide an effective option for enhancing sustainability. This figure shows us how hydrogen produced using renewable source of energy such as solar energy, wind energy, and hydropower. In hydrogen economy, fuel cell is the basic component, and fuel cell is an energy conversion device that converts the chemical energy stored in fuel into electrical energy. And fuel cell was invented in 1839 by Sir William Groves. From Dragon diagrams, fuel cells have a higher specific energy, and this figure is the basic structure of a fuel cell. As you can see, fuel cell has three main components: anode, electrolyte, and cathode. And there are two basic reactions that are taking place inside a fuel cell. Hydrogen oxidized at the anode and oxygen reduced at the cathode. And at the end, water and heat are released as a byproduct. And the application of fuel cell, we can use fuel cell as stationary power supply. We can use fuel cell for transportation purpose. And also we can use fuel cell as a portable power supply. But there are many problems related to this device. The first one is it uses rare and expensive platinum catalyst, and the reaction at the cathode is sluggish, and also there is a stability issue. So in order to widely use fuel cell, we need to solve this problem first. So to solve this problem, two strategies are proposed. The first one is to reduce the amount of platinum content, and the second one is use catalysts made of earth abundant elements. So our study focused on the second strategy. The objective of our study, we focused on a single atom catalysts, and single atom catalysts have gained many attention due to their good oxygen reduction reaction activity. And among different types of single atom catalysts, cobalt nitrogen 4 possess a good activity and superior stability. And the activity could be improved by engineering the coordination environment. So our objectives are to study the effect of nitrogen and sulfur dual coordinations on the electron structure of cobalt in cobalt nitrogen sulfur catalysts, and also to investigate the role of nitrogen and sulfur dual coordination of cobalt in the oxygen reduction reaction. We employed computational methods, so these are our computational details. So this figure shows us atomic structure of our structure. So the gray color stands for carbon atom, the pink color stands for cobalt, the blue stands for nitrogen, and the yellow color stands for sulfur atom. And electronic properties and structural stability of cobalt nitrogen sulfur system. These figures are the partial density of state of cobalt in cobalt nitrogen sulfur system. Figure A is for cobalt nitrogen system, and figure B is for cobalt nitrogen 3 sulfur system. So in cobalt nitrogen 4 system, the magenta shaded area is the cobalt 3D orbital. And also we calculate the d band center. So for this system, the d band center lie on negative 0.7 electrovolts. But in the case of cobalt nitrogen 3 system, the d band center is lie on negative 0.91 electrovolt. This indicates when we incorporate a sulfur atom, the d band center of a cobalt shift below the Fermi level. So the decrease in the d band center of cobalt is attributed to the weaker absorption of ORI intermediates. And this is the charge density distribution. The cyan color indicate the electron depletion, and the yellow color indicate the electron accumulation. So there is a few amount of charge distribution around the cobalt atom. This is due to the coordinated nitrogen and sulfur atoms have a higher electronegativity than the cobalt atom. And also we evaluate the stability of the system by calculating the binding energy of cobalt using this expression, and also the binding energies listed in this table. So as you can see in this table, the cobalt atom has a negative binding energy. This indicates a better stability. And we also calculate the charge on cobalt, sulfur, and nitrogen atom using a Bader charge analysis. So as you can see, the cobalt atom and sulfur atoms are positively charged, but the nitrogen atom is negatively charged. This is due to the higher electronegativity of a nitrogen atom than cobalt and sulfur atom. The absorption energy of ORI intermediates on the model catalysts. These are the optimized structure of a system on which the ORI intermediates are absorbed. So the most active site is the central metal atom. So the most important is the free energy. So we calculate the absorption Gibbs free energy using these three expressions. These terms are the approximation for the vibrational and entropy terms. So this is for OOH, and this one is for oxygen, and this one is for OH. And the absorption, the absorption Gibbs energies are listed in this table, and we also calculate the over potential for these systems. So as you can see, the OH is weakly adsorbed on the systems that contain both nitrogen and sulfur compared to the initial structure, which is the cobalt nitrogen system. And also the over potential for cobalt nitrogen 3 system is lower compared to the other system. This indicates a good ORR activity than the remaining system. The catalytic activity, we evaluate the catalytic activity based on the over potential. This is the volcano plots for ORR. So the plot is gives free energy of OH against the limiting potential. So systems designated by the blue color has the potential determining step for the system designated by blue color is the reduction of OH into water, and for systems designated by the blue color, the potential determining step is formation of OH. So among these different systems, the cobalt nitrogen 3 sulfur system is found at the apex of the volcano plot. This indicates this system has a better ORR activity than the other system. And this is the free energy diagram of the oxygen reduction reaction. We plot the free energy diagram at different electrode potential. For example, for cobalt nitrogen systems at 0 electrovolt, all systems are downhill. This implies the reaction is taking place spontaneously, and the limiting potential, the blue color, the reduction of OH into water is isoenergetic. And at the equilibrium potential, the formation of OH and OOH and the reduction of OH into water are uphill, but the remaining steps are downhill. We also evaluate the origin of the ORR activity based on the barrier charge on cobalt, nitrogen, and sulfur atom, because these atoms are found around the active site. So the green and the yellow colors stands for the barrier charge on nitrogen and sulfur atom respectively, and the blue color is the charge on cobalt atom. So as you can see, the charge on nitrogen and sulfur atoms remain constant throughout the whole ORR process, but on cobalt atom, it shows some change. So our results reveal that the origin of the activity is a cobalt atom. To summarize, the ORR activity of cobalt nitrogen sulfur systems was investigated. The binding energy of cobalt in this system is negative, indicating good stability. The cobalt nitrogen 3 systems has a lower overall potential, which implies a better activity than the remaining system. And the potential determining step is the reduction of OH into water. And therefore, we can conclude that cobalt, nitrogen 3, and sulfur is a promising and precious single atom catalyst for efficient ORR activity in acidic solution in fuel cell. So for further information, I would like to invite you to read this paper. So I would like to thank the organization who support the participation in the 2022 workshop. So I would like to thank the USAfrI Initiative in Electronic Structure, the Innovation Fund of the American Physical Society, the Columbia University, and the East African Institute for Fundamental Research. So thank you for your attention.
Okay, that was very nice recording. Just as a reminder, we will hold off questions until the Q&A session after the next presentation, the next recorded talk. So the next pre-recorded talk is by Dennis Magero, and the talk title is Test of the Orbital-Based Li3 Index as a Predictor of the Height of the 3-MLCT to 3-MC Transition State Barrier for Gas Phase Ruthenium and NN3 Polypyridine Complexes.
Amy, I don't get any audio on this one.
Recording stopped.
Amy, did you choose to share the audio before you started sharing the presentation?
No.
So you can share the sound, but don't optimize the video.
Mm-hmm.
I'm missing the setting here.
Now, when you share, there should be two buttons that say share sound and optimize video. So you should choose to share the sound, but don't optimize the video.
Ah, I see it. Thank you.
Exactly.
Okay, let me roll back.
Recording in progress.
Thanks.
Okay, let me try it again. Now I'm getting an echo. Sorry about this. All right. I'm not quite sure what I should do. Sorry about this.
Recording stopped.
No problem. Yeah.
Could we say that again?
I said no problem. So I think you should just share the sound.
Okay, and
Right?
just continue?
Yeah.
Right, because all right, so.
Recording in progress.
Sorry, could I just present live?
Dennis, is that you?
Yes.
Okay.
Recording stopped.
Yes, Dennis, please present live.
I think it would be better. Thank you.
Okay, thanks.
I'm going to stop sharing now.
Yeah, okay.
Dennis, should we queue up your slides or do you have them?
Yes, Dennis, please share your slides.
Oh, okay.
Okay, he's sharing now.
Okay, great.
Okay, thanks, Dennis.
Recording in progress.
Dennis, you're muted, by the way, in case you didn't realize.
Okay, I'm just uploading the one that is not recorded just shortly.
Okay, great. Thanks.
Recording stopped.
Thank you. Could I start?
Yes, absolutely. Yeah, thanks.
Thank you. I'm Dennis Magero from Malupa University College, Kenya. I'm working with Dr. Sandeep Sharma from University of Colorado.
Could you put it in slideshow mode? Yeah, thanks.
Recording in progress.
Okay, so I'm working on the test of orbital-based Li3 index as a predictor of the height of the triplet metal ligand charge transfer to the triplet metal-centered transition state barrier for the gas phase ruthenium polypyridine complexes. So this work concerns ideally luminescence lifetime of ruthenium polypyridine complexes such as the ruthenium tris-bispiridine. And we're interested in this problem because transition metals actually play a very important role in the design of solar cells, organic light emitting diodes, among other many applications. So the basic idea behind them is that there's an optical excitation leading to an excited state that you require long excited state lifetime of about 1 microsecond, leading to charge transfers. So what you see there is an image of the tris-bispiridine ruthenium-2. There are two ways to explain this particular excitation. The first one is based on the orbital, and the other one is based on the states. Now, on your left, on the left of your screen is the tetrahedral ligand field theory, whereby in the splitting, you can split to T2 g orbitals and the E star g orbitals. So there's some mixing in between here. So you can understand that splitting in terms of this particular, in this way, or you can understand it using the potential energy surface, whereby there's excitation from the ground state to the singlet metal ligand charge transfer. There's intersystem crossing to triplet metal ligand charge transfer. So this can fluoresce back to the ground state, which is very fast. So this work actually works on the idea that there's a barrier here that needs to be crossed. There's an avoided crossing here. This particular barrier is responsible for the long excited state lifetime, and this is what we shall be looking at. Now, as explained previously, from the singlet ground state to the singlet metal ligand charge transfer, there's intersystem crossing. Then you go to the triplet metal ligand charge transfer. If you cross the barrier, then there's a barrier here that we're interested in to be able to calculate the luminescence lifetimes. Now, the assumption that we make here is that luminescence quenching at room temperature is ideally because of the barrier, as explained previously. The focus on this particular luminescence index is trying to find the PDOS LFT explanation of the relative luminescence lifetimes. The difference between those two states, the triplet metal ligand charge transfer and the triplet metal centered, is whether the excited state is either in the pi star orbital, the ligand pi star, or in the metal E star g orbital. Now, when you take the difference between the two, you can be able to correctly predict the triplet, the barrier height for that triplet transition state. Now, the problem is that in this particular state, you find that the orbitals are heavily mixed. It's very difficult to separate the E star orbitals, the T2 g orbitals, and the pi star orbitals. But we've been able to develop in-house build tools. Previously, we've had other indices, the Li1 and the Li2, and we've been able to come up with this index, which is the Li3. Now, this is an example of one of the complexes. You can see here, using our special tools, you can be able to separate the T2G, the pi star orbitals, and the E star G orbitals, which ideally you cannot be able to do without the special tools that we developed in our previous two papers. Now, using these tools and the previous results, we're able to come with an index that we think should be able to work quite well in predicting the luminescence lifetimes. And this is what this work is based on. Initially, we had two other indices, the Li1 and the Li2. And we shall be taking values from the E star orbitals, the pi star orbitals. And what we expect from this particular index is that we'll be able to input the real barrier by calculating them theoretically. Now, this is the performance of the Li3 plotted against the E average. E average is just an empirical measure of this barrier. gotten from room temperature measurements at experiment and 77 Kelvin. So you can see here that for these particular complexes that have the same type of ligands, the correlation is quite good with the almost linear correlation. Now, the issue that we have here is that we do not know the true or the actual barrier height. This is just an estimation. So we want to estimate the barrier heights from theoretical calculations. And this is the idea behind the work. You have an ligand field theory, molecular orbital theory picture. You want to get the luminescence, but how do you get it? First, you must be able to know the triplet barrier. We want to simplify this by doing this theoretically. That is the main objective of the work. Now, what do we know about the molecular orbital index 3? That this is a molecular orbital prediction of the barrier height. As seen previously, there's good estimation or agreement with bidentate polypyridine complexes, as explained initially also, is that E average is not the true barrier. We seek to calculate the true barrier from the calculations that we'll be involved in. E average is also guessed because we are taking it from the liquid nitrogen temperatures and the room temperatures. And the objective, of course, is to calculate the true barrier height at the same level that we developed the Li3, that is the same orbital, the same basis sets, and all the factors that were considered. Now, the challenge that we face is that the triplet surface has several transition states, and you need really special tools to be able to predict the transition state, because the transition state can be as a result of another pathway and so on. So really, do you have the correct transition state or not? To do this, a 2D scan will be done, whereby two trans bonds will be dissociated to be able to determine the transition state. So these are just some of the highlights of the problems that we need to connect the products and reactants by proving some of the ideas that have been highlighted here. Now, the computational details here, we have Gaussian 09, the same as what is used in developing Li3. B3 LEAP, you have those basis sets, the ECP, the ultrafine grid. We'll also use OCA and that without the auxiliary basis sets. Now, this is data from supplementary material of reference 1, which is here. You can see that from that material, this was the starting point. This is a trans dissociation. And we want to do the same to see whether we can be able to replicate what was done in this work. So you stretch two bonds symmetrically across, and these are the results. So one is in gas phase, and one is in solution. So you expect that there'll be some Jantella distortion as you move from the triplet MLCT to the triplet MC. So in gas phase, it's almost symmetric with a C2 dissociation. In solution, you can see as you move across, this is at 0. This is the intrinsic reaction coordinate scan. You can see that the bond lengths here are short, triplet metal ligand charge transfers. You move to the triplet metal centered. There is a Jantella distortion whereby you have two long bonds rather, and 4 short bonds. Now, when you look closely at this, when you look quite closely at these particular results, you find that it's not really a trans dissociation as expected. It's actually a cis dissociation, and these are part of the challenges that we come across while doing the transition states. So this is just a comparison of some of the experimental values, although theoretically this has not been done. Having done that, this was applied to the geometries that we have by optimizing, getting the triplet metal ligand charge transfer state by simply optimizing the ground state and changing the spin to 3. We're able to get these particular results with the bond being elongated. So from the triplet metal ligand charge transfer, we do a 2-dimensional scan. From this, from 1.90 to 2.50 angstroms. This range is long enough to make sure that we cover the entire potential energy surface. And the aim of that scan is to be able to identify the triplet metal centered and to be able to identify the triplet transition state. So this is a scan that you're talking about. This is the bonds that have been stretched, and all of them are similar because it's symmetric stretch. And these are the results that we have. So this was plotted using an in-house build program. This is a two-dimensional contour plot. You can see that you're moving from triplet MLCT to triplet MC as you stretch. And you can be able to identify the transition states. There is one here with the yellow hat, and there are two that are symmetric with the pink hat. On the left here, you can see that you expect to go through a barrier. So there's a triplet MLCT, there's a triplet MC. As you move from here to here, there's a barrier here, and you should be able to identify a transition state here. The only problem that we face now is that do we have the correct transition state or not? Because it's possible to find a transition state, but is it the right transition state or not? So from the analysis of the RC, with the plot of the bond lengths, at zero is this zero is the transition state. And on the left and the right is the triplet MLCT and the triplet MC. What you find about this particular plot is that this plot is really symmetric. And the question is, what do we deduce from this? This is just a plot of the IRC. Now, from the plot here, we see that there's overly large symmetry. You can see that both points are the same. We came to a conclusion that there's something called a pseudo-rotation between the triplet metal-centered Jantella distorted structures detected with those close to the expected transition state. So ideally, we have a transition state, but it is not the right transition state because of the challenges that we faced initially. So we expect to solve this problem by using alternative algorithm because you are quite close to the transition state, but you are not at the transition state that you want. By using other methods, and we intend to use the large elastic band, which is in Oka, using the same basis sets and all the other inputs that we used for doing that. So the conclusion is that new difficulties were encountered in this project due to near-lying transition states shared by more than one reaction pathway. We are saying that the transition state might be right, but it might not be the correct for the pathway that you want. Actually reaching up to here, there are many techniques and many challenges that we've been able to overcome. And once we get the correct transition state, we should be able to proceed and work with the LI3. So the new calculations have been started running with Oka, with no auxiliary basis set, and B3 leap /G, which is similar to what we expect or what we did in Gaussian. So I'd like to acknowledge the USAfrI initiative. I'd like to acknowledge Professor Richard Martin, Professor Mark Cassida, whom we've been working with, colleagues, Dr. Aladin Darkouth of University of Mosul, Pierre Girard, who has been giving support as we use the clusters, Alupa University College for the study leave, the assessment for the many training and schools that have gone, Dr. Sandeep Sharma, and all USAfrI organizers. Thank you very much for listening to me.
Thank you very much, Dr. Magero. That was very nice. Are there questions from the audience?
Yes, I have a question.
Yes, go ahead.
Thank you, Denis, for your presentation. That was really nice. Thank you. I just have a question about the solvent you use. Do you use implicit solvent or explicit? And if you use implicit solvent, is it that solvent that yield Jantella distortion, or do you have an explanation of the occurring of that distortion?
Thank you, Anne, for the question. Actually, for the calculations, all of them are being done in gas phase. And the reason for this is that when you are developing the luminescence index 1 and the luminescence index 2, and also the luminescence index 3, all the calculations, we did them in gas phase. So all the calculations here in gas phase, because if you do it in solvent, when you're developing the luminescence index, even 1 and 2, the problem even becomes more complicated because there are factors that come in, for example, the rate constants and so on that you have to consider. So that becomes even more complicated. Where you see we've been using solvent is we've been doing that for comparison purposes. But of course, in solvent, you can see that the genitalia distortion is more produced compared to when you do it in gas phase.
Thank you. There's a question from Dr. Young in the chat. From the conclusion in Asnake's work regarding the hybridization between 2p and 3d, kindly, how many electrons in the valence band in the CO and 3sc? What type of hybridization is happening, and how do the valence electrons distributed in the hybridized orbital?
I have to read that.
Okay, it's a great question. Hello, everyone.
Okay.
Hello, everyone.
Hi, go ahead.
Okay, it's a great question. The hybridization occurred is PD3 hybridization is occurred, and the electrons are distributed around nitrogen and carbon atoms.
Great. Thank you. I think we're a little bit over time. I know we have a little break, but I do want to have time for there's going to be a Zoom picture after this. But as chair, I'm going to take the prerogative of one last question, if that's okay, for Dennis. That was very beautiful work. Did you check for wave function stability, especially around the transition state where when you were checking the two different spin states?
Thank you for the question. We did not check that. That will be something perhaps to consider. And of course, those are ideas we welcome if it would really help us to get the correct transition state.
Yeah, I think that would be an interesting, especially for the Jantel or the stored structure.
Yes. Okay.
Thank you.
Thank you.
Okay. Well, yeah, so I will let Dr. Young now take over for the group picture.
Okay, thank you. Actually, full disclosure, I don't have a doctorate. It sounds like you're talking to my mom or my dad. Just
sorry, it's the same one.
I'm an imposter. Okay, yeah, so I will ask everybody to please turn on your cameras so I can take a group photo. And I will, oh, that looks really nice. And so it will go fastest if everyone holds, I'm looking at my iPad, if everyone just holds a smile for like 90 seconds. Otherwise, I have to call you out by name and say that you look too serious for this photo. Yes. Okay. Sinead looks great. Paul, you still look serious. Mr. Adibambo, that's better. Okay. Thank you. I am turning into my dad. I was thinking about this. Let's see. Dennis, you look great. Is that Amisi? Is that Amisi Safari? Oh, yes. You look too serious. Please smile. Yes. You look very serious.
Hello.
Yes, okay. Can you smile, please? Nice, thank you. Very good. Next group, let's see. Steve got a haircut. It looks very good. Victor, you look nice. Can you, let's see. Pustana, you look good. Maram, oh, looks very, very nice today. Sarah, is your camera off? And let's see. Lala, there's Sarah. Okay, great. Now we see Sarah. Who else? I think, Chengjing, I think. Oh, Fatima, is your camera off? Can you afford to turn on your camera? There's Edward. Good morning, Edward. Nice to see you. Okay, let's see. Fatima, I don't see your picture, but I have a nice photo from you, so I might cheat and put that in this. There's Mehmet. Very nice. Winfred, I see you. Okay, very good. All right, let's see who else. Last one. I think everybody looks great. Oh, there's Miss Finn. Good morning, Miss Finn. Afternoon, Miss Finn. Perfect. Okay, Mehmet's changing his chair position and his camera. Now we could smile. Okay, perfect. All right. Thank you so much, everybody. I'm done now. You can take a break. Thank you.
Thanks, everyone.
See you back here in 10 minutes.
Ami, I think you are muted.
Yes, you're unmuted.
Okay, so now can we start, or it's 5:30 here in Bordeaux?
Yeah, I think it's the right time to start.
Okay, so good morning or good afternoon, everyone. Welcome back to our second session for today. So in this session, we are going to talk about the surface functionalizations and the low-dimensional systems. We are going to have 4 speakers. They are all pre-recorded. So we are going to keep the question at the end of our session, and then at the end we will have the question and answer sessions. So it's a pleasure for me to introduce our first speaker, who is going to talk about the ab initio simulation of copper oxide nanowires and cluster on titanium dioxide. So ladies and gentlemen, please help me to welcome Dr. Victor Mengwa from Alupe University College in Kenya.
I'm Victor Mengwa from Alupe University College, and my would-be host and my host will have been David Brendergast from Lawrence Berkeley National Laboratory. The title of my talk is ab initio simulations of nanostructured copper oxide on TiO2 and clusters. Now, solar energy is clean, renewable, and inexhaustible natural source, and this energy is quite abundant. 1 hour of solar radiation is enough for our annual world consumption. Now, the solar conversion efficiency is usually very slow and inefficient, and it ranges actually between 14. The conversion rates at the highest conversion rates range between 14 and 19% on marked crystalline silicon solar cells. So therefore, because of that, we require a photocatalyst to speed up this reaction. And usually transition metal oxides are catalysts. Now, anatase TiO2 exhibit high photocatalytic activity. The bulk anatase TiO2 has tetragonal lattice, while the 101 surface is the most stable and dominant plane. TiO2 has a band gap of 3.2 electron volts, and therefore it absorbs in the ultraviolet region, which actually constitutes 3 to 5% of the solar spectrum. Therefore, you need to modify TiO2 to extend absorption to visible range and suppress it. The oxides that are usually coupled with the TiO2 to improve its photocatalytic activity are the copper oxides, the cuprous oxides, which is a p-type semiconductor with an energy gap of 2.1 electron volts, and used as a sensitizer to extend absorption to visible range. The cuprous oxide as a cubic structure. The cupric oxide is also a p-type semiconductor whose energy gap range between 1.4 to 1.7 electron volts. It's usually used for fabrication of the p-n heterojunctions for solar energy applications. The bulk CuO has a These coupled semiconductors on their own have properties that make them suitable for these particular functions. The copper oxides are actually good catalysts. They are cheaper than noble metals. They have narrower band gaps and they are non-toxic. While TiO2, which is employed as substrate, has a powerful oxidation ability, superior charge transfer characteristics, stable, non-toxic, abundant, and cheap. The coupled oxides are actually effective core catalysts photocatalytic we employed the quantum espresso code that utilizes DFT with the planars and pseudo potentials. The calculations were carried out with GGA plus U 4.2 volts for TI3D and 5.2 volts for copper 3D states. TI2-101 at the surface is translated from the bulk. It has a vacuum width of 14 angstroms. The copper clusters are actually calculated from the bulk copper oxides, or they are prepared from the tetragonal copper cluster with the adsorbed oxygen molecule. The nanowires and clusters are actually adsorbed on one side of the slab and relax until the force on each atom is smaller than 10 raised to the power of negative units. Methodology. Now, the thermodynamic stability calculations are carried out with respect to oxygen pressure. This combines the DFT energy and the chemical potential to calculate the Gibbs free energy. The formulas for doing these calculations are indicated for bulk copper oxides and for the coupled nano structures that are indicated there. The first stability of copper oxides. Now, when the ab initio molecular dynamics calculations are carried out, it's found out that at room temperature, CuO is most stable oxide. Cu2O is easily oxidized to CuO at room temperature. At high temperature above 617 kelvins, copper is actually most stable, and you can see this when you look at this particular when you look at this what the figure that has been drawn here of the logarithm of oxygen to the base of 10, the logarithm of the oxygen to the base of 10, oxygen to the base of 10 against concerning the CuO nanostructure and the clusters on TiO2, it's found out that CuO nanowire is most stable compared to clusters on TiO2. The Cu3 and Cu2O are the most dominant frameworks, and the most dominant and most copper atoms are actually high. The most are over coordinated. Four are over coordinated, and they are actually 4 to 5-fold coordinated, while most of the copper atoms are actually 3-fold coordinated. So the most dominant, the nanowire has actually a planar symmetry on TiO2. Similarly to CuO, the nanostructure, the nanowire is actually the most stable on TiO2. The clusters are less metastable, are less stable than the nanostructure. Nearly all copper atoms are over-coordinated except for one that's 4-fold coordinated to copper, which is comparable to what we see in the bulk CuO. Again, the Cu dominant. The thermodynamic stability of the copper oxide nanowires on TiO2 was also carried out and it found out that at all temperatures and pressure, Cu2O nanowire on TiO2 101 surface is thermodynamically more stable than the cupric TiO2 oxides. This is attributed to CiO2 being more symmetric and more ionic, and also having lower surface to CuO. Now the p-dose of the cuprous TiO2 nanowire is shown here. You see that the states that the energy gap has actually been narrowed to 1.62 volts, and this is because states have actually extended to the energy gap. The electron transfer from the Cb of Cu2O to Cb of TiO2. Similarly, there is whole transfer from the Vb from the valency band of TiO2 to the valency band of Cu2O. Therefore, we are seeing here actually that electrons are transferred to the conduction band of TiO2, while holes are actually transferred to the valency band of Cu2O. This actually facilitates, this actually leads to charge separation, and therefore it's actually suppresses oxidation. We see a control case in Cu or TiO2 in the sense that we have empty copper 3D states near the bottom of the conduction by the minimum, and holes in the valency band and electrons in the Cb of TiO2. All of them transfer actually to CuO. Therefore, we don't see that separation like what we have just seen in Cu2O TiO2. Now, the conclusion is that the copper oxide nanowires are more stable than clusters on the anatase TiO2 surface. Cu2 nanowires are thermodynamically more stable than Cu nanowires. These are the variants with what we see in the bulk, whereby the copper, oxide, whereby the copper oxide that's most stable is CuO. Now we also see field states in Cu2O and CuO nanowires belonging to the copper oxides. The lowest lying empty states belong to TiO2 in Cu2O nanowire in the structure that's coupled with Cu2 nanowire, and to CuO in the structure that's coupled with the TiO2. Now, field states extend into we also observe that field states extend into the titania energy gap, reducing the gap of the system by over 1 electron volts, and therefore it means shifting its absorption actually to the visible region. Cu2 again we can actually see from what we've just discussed that Cu is more effective in charge separation than CuO on TiO2. Again, thank you for your audience.
Thank you very much, Dr. Victor Mengwa, for the nice talk. Up next is Dr. Sara Abass. She's going to talk about a density functional theory study of the formation of electron paleron in hematite. It's also a pre-recorded, and
Hello, I'm Sara Abass. I'm going to present some results of this work I have done with Agopi Ridwan from Nigeria and Dr. Nicola Suriani from ICTB. We try in this research to investigate the formulation of electron paleron in hematite using a density function theory study. We study crystal structure of hematite starting by the results from Nicola et al. When a big ordinary research on hematite structure have been done. The hematite structure shown in this figure above. For a unit cell and 2 by 1 by 1 supercell hematite, this material an antiferromagnetic material with hexagonal crystal structure. We start with the lattice parameter from Nicola et al. 2014 when A equal B is equal 5.07 angstrom and C equals 13.90 angstrom. And for 2 by 1 by 1 supercell, it is A equal 10.14 and B equal 5.07 angstrom and C equals 13.90 angstrom. We have looked at the electronic structure of hematite. It is an antiferromagnetic material. We look at the band structure at the majority screen and minority screen, which was used to produce a band gap. In this screen, there are a gap in the pulse up spin and down spin of the band structure. For this material, which agree with the band gap with the previous literature. Density of a state also calculated to look which orbital contribute to the band structure, as seen in the up spin and down spin density of a state. We found the oxygen it is most represented in the valence band, while the ion with a d orbital it is most presented in the conduction band. And when we introduce an electron in a system of this hematite material and we roll that is the calculated the band structure again in this case. We use this unit cell of hematite structure and shown a Fermi level in the gap in the both up spin and down spin band structure. We able to see a single band with stake of an electron polaron in the gap. In this system, we phenomena also observe as it was good to formation electron polaron. We also look at the third case of having an electron in the system. We study density of state and we show clearly the band gap around it. And it also saying a state in the gap and clearly states that is the contribution to be an oxygen with the B orbital in the valence band and ion with the D orbital in the conduction band. And when we decide to look at the supercell of hematite structure, we starting by 2 by 1 by 1 supercell. We try to see a band structure of this material without a high electron and able to see all the band gap. And when we have an electron to this material, 2 by 1 by 1, we realize that a single band have introduced in the band gap, which will be as a result of the formulation electron of polaron in this gap of this system. When we go further and we look at the density of state of 2 by 1 by 1 supercell structure, we see a result and information of the state in the gap and also share the situation of electron polaron in this system. And when we decide to look at the charge density of the system in the case of 2 by 1 by 1 supercell hematite, it is for upspin charge density and downspin charge density of the system with and without electron. And we show clearly that an electron having in the system, the electron are located around an ion atom, while a part of electron it is go some part of the oxygen atom. But the measuring that some of these electrons are localized in the ion atom. But it's quite challenging that the particular electron is localized in the two different ion sites, while research shows that is an electron localized in the single in the ion side, and work study while excited having an electron localized in the two ion atom in the state of one ion instead of having in the one ion atom. And in the acknowledge we try to science International Center for Theoretical Physics and East Africa Institute for giving us an opportunity to do this work, and also for ASISMA, and also we thank ABS for inviting us to give this talk at this workshop. Thanks all.
Thank you, Dr. Sara Abass, for your presentation on the formation of the electron polaron in hematite. The next speaker is Dr. Michael Atambo. It's also pre-recorded presentation and is going to talk about automated convergence calculations with AIDA.
Good morning. My name is Michael Atambo from the Technical University of Kenya in Nairobi. My host is Renata Wentzcovitch from the Columbia University in New York. I'm going to speak to you about automated convergences for many body calculations with AIDA Yambo. I'll start with a bit of a background on this issue. So modern electronic structure calculations are quite robust in terms of output. So if we limit ourselves to DFT, there's over 10,000 papers that cite the work of Kona and Sham, and the trend is only set to increase. So there will be an acceleration in terms of output. And all the factors that would influence this point to this fact. If it's the codes, they are increasingly more sophisticated. If it's the personnel, they're getting better and better specialist training. And the computing resources are now approaching the exascale in terms of performance. And none of this is going to reduce in pace, so to speak. Now, the traditional approach to computing and materials research was one graduate student paired with a senior scientist working on one or two materials. However, this may not necessarily be what will be present in the future. So a lot more work can be done and can be made possible using a much smaller number of domain experts. This is from advancements in techniques and methodologies. What am I hinting at? I'm talking about high throughput computing. So new techniques have been proposed for doing large-scale computational work, and these techniques have been applied to solar energy materials, exfoliation, and similar groups of materials for specific applications. Now, once this large-scale work has been done, it turns out there are multiple benefits to be had after the fact. So the initial outcome of the work may have been reached. However, since there is a lot of data that has been found, it has to be stored in some way, typically in a database. So it turns out we can do data mining on these databases that have been created and find materials appropriate for applications that were not originally thought of. And in addition to that, we can be able now to train predictive machine learning models that can extrapolate from known to unknown materials or properties. So those are benefits that come after the fact, that when we have already collected significant amounts of data. Now, specifically getting back to many body calculations, there is a challenge that stands in the way before we can be able to run high throughput calculations for GW. And one of these is the automation of the GW calculation itself. And before you can get to the automation, the idea of convergence, since many body calculations require that you first converge all the relevant input parameters before you can be able to get physically meaningful output. Now, for DFT, the typical approach has been to use so-called safe parameters. What these are effectively over-converged input variables that will use a lot of CPU time. The other thing that has been that should not be done is to report under converged results. However, ad hoc heuristics have been applied. However, since these are not very systematic, they are not very broadly applicable. One other issue also needs to be considered when thinking about the idea of automated convergence. So this is a problem of slow convergence in GW. So it's known to present a characteristic convergence rate of about 1/x. So this can be a problem because if it's converging really slowly, it becomes somewhat tricky to reason about whether a calculation is converged or not. And the fact that there are multiple such parameters in GW makes it a non-trivial multi-dimensional problem. So what can be done? This problem has been addressed by the work of Van Zetten, who talked about methodologies for working with GW in high throughput scenarios. So it turns out that of the parameters that go into a GW calculation, there is a select group of parameters that can be thought of as being independent. And among this, there will also be a few or a pair that will be interdependent, and they need to be treated as such. Now, the work that we did was not built from scratch. It actually used the work of a framework known as AIDA, and this is an open source framework that provides a platform for managing, preserving, and disseminating the results of simulations, and it provides a means to capture end-to-end all the input parameters and all the outcomes of a calculation in what is known as a provenance graph. Now, that said, assuming you're able to run your simulation with AIDA, this already implies that you have achieved some level of reproducibility, since all your inputs and the resulting outputs were captured on the provenance graph. And if this is shared with the rest of the community, it becomes extremely trivial for everyone to reproduce your work. Now, the way you would work with AIDA is by developing as a plugin to interface with the physics code that you're using, since AIDA itself only provides a framework for doing the automation. It doesn't do the actual DFT or many-body calculation. And it also provides a means of capturing domain-specific knowledge. So using what we call work chains and workflows in AIDA, you can be able to capture knowledge that resides typically with the expert. It is free, the framework itself is free, and it's developed at EPFL Lausanne in the Marvel group. Now, the physics code that we're using is YAML, that implements many-body theory, and it has support for studying electronic and optical properties, and it is freely available. So this is what we developed a plugin for to work with AIDA. Now, what can you be able to do with this plugin? You can be able to run highly accurate many-body calculations with it using YAML in the background, and it helps us to encapsulate and capture non-trivial knowledge that goes into running many-body calculations. So whether it's the fact that you have to use multiple codes, some to provide inputs to your GW code, all of them having their own input parameters, and this being done in multiple interdependent steps, this broad set of skills have been captured and added to the plugin. Now, in addition to that, we have some other capabilities that are useful, including the fact that you can run error-tolerant calculations. If you're running large-scale calculations, it's impossible for you to monitor every single calculation and correct for trivial errors. So you will want your framework to be able to correct trivial errors for you. So this plugin provides that facility for running GW calculations. So these trivial errors will be things like queue time in a HPC facility, parallelism or memory issues, and so on. In addition to this, we have some domain-specific knowledge captured in our convergence workflow, with both 1D and multidimensional. So the 1D convergence workflow can be able to pick one parameter selected by the user and converge it with respect to the electronic gap. And the same thing can be done for the multidimensional convergence approach, where we have multiple selected parameters that go into the GW calculation being converged in an automatic fashion. So all of them systematically are swept through until we have converged parameters, which are then reported to the user together with the result of the calculation. You can be able to find this plugin on GitHub and introduce and install it, of course, in your AIDA installation. So this is one such result from a multidimensional convergence calculation, and this particular example is from titanium dioxide, and we have the 5 critical parameters that go into a typical GW calculation in YAML making an appearance here. So we converge the quasi-particle gap with respect to the K points, the FFT grid, the number of bands, and the cutoff for the screening. And the last parameter, the bounds, you can see has been repeated because we expect these two parameters to be interdependent. And when one changes, you always have to check that there is no significant alteration to the other interdependent parameter. So this is available, and you can be able to use it for your work. Of course, a lot more is still going on with the plugin, and it still continues to be developed. So right now, the key person is now Miki Bonashi, since I left Modena. But further work is going on with increasing the sophistication of the 2D convergence approach, and this work is already available for use. We believe that you can be able to accelerate your large-scale characterization of materials using many-body theory while being able to improve reproducibility of your work and share it with others, since AIDA provides a way of picking bits and pieces of your database of outputs and sharing it with the rest of the community, either in a publication or some addendum to the publication. I'm also currently working on other things, including materials for environmental remediation and catalysis. And with that, I want to thank you for your time and attention. You can always reach out and ask questions or have a discussion with myself at any point. Thank you very much.
Hi everyone, I'm Gugulethu.
Thank you very much, Dr. Mike Atambo, for the very interesting talk on automated convergence calculations. Our last speaker is Gugulethu Nkala. She's going to talk about on the average local and electronic structure of NASICON-type structure.
Hi everyone, I'm Gugulethu Nkala from the University of the Witwatersrand in Johannesburg, South Africa. I'm working with Professor John Ray from the University of Washington on the average local and electronic structure of NASICON-type lithium aluminium dysprosium titanium phosphate. A brief introduction on lithium titanium phosphate as a solid state electrolyte. The structure of lithium titanium phosphate consists of TiO6 octahedra that are corner linked to PO4 tetrahedra, forming a helix that extends mainly along the C direction. The mobile species lithium cations can occupy either the 6B or the 18E site. In this case, the 6B is more energetically favorable. The net ionic migration is from the 6B site through the lateral phase into the 18E cavity and into the 6B site on the adjacent ribbon. Although this structure can allow for fast ionic migration, it has a reported conductivity in the order of 10 to the negative 7 Siemens per centimeter, which is too low for applications as a solid-state electrolyte. Therefore, doping with allovalent and isovalent cations has been employed as a strategy to improve the ionic conductivity of LTP. The highest conductivity in NASICONs has been reported for 15% aluminium doped LTP in the order of 10 to the negative 4 Siemens per centimeter. This is attributed to the tuning of the bottleneck size that allows for faster migration of lithium due to lower activation energies and increased bottleneck size, as well as increasing the amount of charge carriers. The increase in the amount of charge carriers is due to the excess lithium ions that are added for charge balance that then occupy the favorable 36F sites within the 18E cavity. In this work, we have formulated an aluminium and dysprosium co-doped LTP system, which has exhibited an ionic conductivity in the order of 10 to the negative 5 at room temperature. This has been an improvement of 2 orders of magnitude relative to the parent structure of LTP. We are therefore investigating the effects of doping on the average and local structure via synchrotron X-ray diffraction, Raman spectroscopy, small box modeling of the paired distribution function data, and experimental and computational XANES. Synchrotron XRD has sought to provide information on the average structure of LADTP. The highest intensity peaks in our XRD pattern have been indexed to the rhombohedral NASICON-type LTP structure. This suggests that we do have aluminium and dysprosium successfully incorporated into the structure, although this has a solubility limit shown by the formation of secondary phases such as dysprosium and aluminium phosphate. The formation of dysprosium phosphate is due to the size disparity in the ionic radius between titanium and dysprosium. Therefore, replacing titanium with the relatively larger dysprosium as well as aluminium simultaneously forces only a specific amount of these cations into the framework. Raman spectroscopy has also been employed for further phase identification as well as understanding the local structure around the phosphate and iron groups. The vibrational spectrum of LADTP has been indexed to the NASICON-type rhombohedral structure, which is what has been reported from XRD, as well as no detected phases of dysprosium and aluminium phosphate. The spectrum consists of external modes that are due to phosphate group translations and pseudo-rotations, as well as the metal-oxygen translations. Above 380 wave number, we have the symmetric and antisymmetric bending and stretching nodes of the phosphate and iron groups. This technique is insightful in terms of understanding these phosphate and iron group changes, but it has not provided significant information on what happens to the metal-oxygen regions. As such, employing paired distribution function data will unravel the secrets that were buried underneath the Bragg peaks from our XRD data to then provide more information on the average and local structure. For the small box modeling has been used as a model for paired distribution function data to gain insight into the existence of potential minor crystalline phases, as in this work, the formation of amorphous phases that were not detected from X-ray diffraction, or the existence of local distortions wherein the average structure does not agree with the local structure. In our case, small box modeling of the LADTP system using the rhombohedral structure that we obtained from Bragg data has shown somewhat of a reasonable fit at higher R. But considering the residual, as we go further towards lower R, we notice a greater discrepancy. This suggests that the model that we obtained from XRD, our rhombohedral model, is insufficient to account for what we observe at low R. This is a zoomed region of from 1 to 10 angstroms, showing the misfit between our rhombohedral model from X-ray diffraction as well as our experimental data. Doping with larger cations such as tin, hafnium, and larger M3+ cations has been reported from DFT calculations to induce local triclinic and monoclinic distortions. However, this has not been shown from experiment. Therefore, employing this strategy, we have applied a monoclinic structure to see if we can describe our local structure. And indeed, we do find that at low R in the region 1 to 10 angstroms, our data is best described using the monoclinic P21/N model analogous to the beta iron sulfate. Using these models, we have then compared experimental and computational XANES to hopefully link PDF to XANES. Our dysprosium phosphate in the tetragonal phase is the phase that we detected from Bragg data. The information from paired distribution function has also been used to model dysprosium phosphate using the monoclinic structure. We have overlaid our experimental LADTP spectrum as well as a sum of both of the monoclinic and tetragonal phases that were obtained from Bragg data as well as the PDF. Using only the tetragonal phase from Bragg data showed a significant discrepancy in the higher energy range, suggesting that this model could not fully describe what we observed experimentally. Therefore, using linear combination fitting, we obtained the ratio of 84% from the tetragonal to 16% of the monoclinic dysprosium phosphate to get what we currently have as the best model describing what we observe experimentally, especially at high energy. Going forward, we seek to further improve on these computational calculations to then best match our experimental data as well as calculating the densities of states to understand the nature of our Zane spectrum, thus giving us information on more local influences of dysprosium doping on the structure of lithium titanium phosphate. Our conclusions: we have successfully formed an aluminium and dysprosium co-doped system that has an average rhombohedral NASICON-type structure. However, this has also resulted in the formation of dysprosium and aluminium phosphate secondary phases. Paired distribution function small box modeling has shown a discrepancy in the average versus the local structure, reporting for the first time the existence indeed of the monoclinic distortion at low R. Zanes has shown a reasonable agreement between our computational and experimental data, which supports the existence of dysprosium in a monoclinic environment, as only one phase, a secondary phase, does not fully account for our experimental data, especially at higher energy range. And with that, I would like to thank these organizations and thank you for your attention.
Thank you very much, Ms. Gugulethu Nkala, for the presentation. It was nice. So now we are now in the question and answer session. If you have question, then okay. So there is a question for Mike.
Yes, I have a question. Michelle, is that am I allowed to ask?
Yes, you can ask, and then I will read the letter, the one on the chat.
Okay, thanks. So the question is for Sara Abass. I hope I'm pronouncing your name correctly. And it's concerned about the you showed the electronic structure, band structure for spin up and spin down using DFT plus U. And I didn't see that much difference between the spin up and the spin down. And maybe that's correct. And maybe can you give us some information about that? And if you expected to have like some difference, basically like a charge moving into one of the spins.
Sara?
Yes. Yes. Sorry, can you say the question again?
So like when you show the band structure for the electron polaron in the gap, you show two band structure, one for spin up and the other for spin down.
Yes.
But they look really similar.
Yes, that's what we said. We said there is no difference between them. Yeah. That's what we got it. Yeah.
But did you expect the the charge to be only in one kind of spin?
And yeah, and that is when we compare it with the literature, we said this is what we got it from the other literature. It's the same thing what we have it.
Okay.
Yeah.
So, and it doesn't depend on the initial guess. If you polarized in the system to start with, does it favor some polarization, or it remains like evenly distributed between spin up and spin down?
Yeah, it's supposed to have a different, yes, that's what you said, yes?
Yeah.
Mm-hmm. Yeah, but that is what we got, is that there is no that is much different.
Okay.
Yeah, but we're still working on it. We didn't finish from that work.
Perfect.
Yeah, we try to have some difference.
Okay, thank you.
Yeah, pleasure.
There is a question from the USAfri director for Mike. Is it the GW or is it GW or G0W0?
So what I was referencing is many body as implemented in Yambo, so J0W.
Okay, thank you for that. Do you have questions? If you have questions, unmute. Or you can use the chat line, or you can unmute yourself. I have question for Victor Mengwa. You choose the surface 101. Is there a specific reason for that, or why didn't you choose other surface like 1-1?
Yeah. Yeah, thank you, Felana. It is the most stable and the dominant plane on NATI's TiO2. That's why we chose 101 surface.
Okay.
Thank you.
Thank you for that. Next questions.
Okay, great. Thanks, Felana. I think we're probably drawing on now anyway.
Yeah,
so
yeah, that's what I'm checking. Okay, thank you very much, everyone. Thank you. Let's thank all our speaker for today, and we can use the reaction in at the bottom of your screen to thank all of our speakers.
Great. Thank you, everyone. And thanks, Felana, for chairing the session.
Thank you very much. It's a pleasure.
So I have a few small announcements. So the first is, for those of you who might not have registered, please do so with the tiny URL link, which will be posted in the chat. So we'd appreciate if you do register, so then we have a record of everyone who was here and participating. So that's the first. And then a big thank you. So those of you who might have attended our previous workshops might have noticed that today went a lot smoother. And the reason for that is that we had an awful lot of help. So we had a lot of people behind the scenes helping with the Zoom and all the tech. So I'm going to call them all out, and I'll thank them every day because they deserve to be thanked every day. But Jingyi, Sunday, Justine, Chenzing, Hanjing, and Ji. So if you want to turn your cameras on, you can, and say hi to everyone, because you've all been kind of running around in the background. So you can say hi to everyone, and thank you very much for all the work you've done today. And a huge thank you as well to Amy, who you probably all know and I've heard from several times. She's the mastermind behind making sure this is all also operating smoothly. So with that, I'll say we'll close today. And thanks again to the chairs and the speakers, and we'll see you at the same time tomorrow. So have a great evening, morning, rest of the day, everyone.
Okay. Thank you very much, Sinead. Sinead, when are we taking a group picture?
We did it today, but we can do another one tomorrow, maybe.
Okay, no problem.
Yeah.
Oh, Omo, I can put you in with Photoshop. I have Photoshop and I know how to use it, so
Thank you.
I will do that. Thank you.
Thank you very much.
Bye, everyone.
Okay.
Thank you.
Thank you
So,
very much.
oh,
be open for a while, so feel free.
yes, if you want to hang out and talk, you can.
Thank you.
For all of the travelers, if you hang out here, I have a few announcements for just the people who are traveling. It won't be relevant for everybody. Everybody can take off or, go to a breakout room if you like. So let's see. Garu, I don't see you on my spreadsheet of contact information, so I'm going to email you a link, chat you a link, and let's see. Okay. Let's see, here you are. Okay, so this is just for people when they're traveling, so that you can all get in contact with each other while you're, while you're in New York. I figured you would want to know how to contact each other. And so I'm asking people if they want to be contacted to fill that form out so we can share that with everybody else. And let's see. Yes, that's the main thing. Also, if you are here and you are presenting tomorrow, I believe I have uploaded all of the slides that I've received. So I'm going to post a link to everybody here. If you don't see your slides, let me know. Please email me. And then there's also, so we're not posting any videos yet so that they feel live, but your talk slides should be up. And also, we received only a few posters for printing for the electronic structure workshop next week. So when you get a chance, please upload those so that Jingyi has time to work them into the queue for the workshop. So let's see. Okay. Thank you, Vanessa. All right. Any Jingyi, is Jingyi here? Yeah, she's here. Is there anything else, Jingyi, that you need? So let's see.
I think so far everything is good. And I just have a question about the recordings, because currently we are having a recording for all the whole day one workshop, which is one shot for every speakers, every talks.
Yes.
Do I need to cut for
I can
separate
do
talks?
that. I can do
Okay.
that unless you want to do it. I was in and out, so I might miss, something. So if you would
Yeah, I
like to
can do
do
that,
that, that'd be
actually.
great. Okay. And
Yeah, sure, no
then
problem.
what I sometimes do is use the time code to put on YouTube, so there's a table of contents in the video.
Mhm. No
So,
problem.
but I can also help you do that. Let's
Yeah,
see.
I
who
can
else.
deal with that later this afternoon. It's okay.
Okay. And let's see. Is Catherine still here? Let's see. And Justine, are you still here? Yes. Okay. Great. So if Catherine and Anne are still here, you could add your name to the contact sheet. So that's just for when you're traveling.